All right, let's do the audio check then. Welcome everyone. I see two viewers. That's good. That's good. You should have sound now. So I know my moderator's here, so thank you for joining me. And that's weird. That's weird. Apparently everyone left, or the stream just crashed. I don't know which one of the two it is, but at least I'm here. So there it is. Whoop, there it is. So that's perfect. All right, so at least I'm audible then. It's just that we have to see what's going on. So I have no idea why I'm getting all kinds of error messages from YouTube that doing the lecture. Yeah, I'm doing the sound check. Mm-hmm. All right, so I'm back. Do you have your window open? How do you mean, do I have my window open? I have my starting soon window open, since we haven't started yet, and there's some minor issues here to solve, since we're having issues with our -20 freezer. Yeah, it's a pain. The warm weather here is really taking its toll on the equipment that we have. So apparently, like the -20 was at -3, and then everyone panicked, and the guy from the -20. Do you have? Yeah. Oh, like that. So you can hear that. All right. You know the analog one. Okay. Yeah. I will close my analog window. Yeah, the big hole in the wall. True. That's open. So that should be closed now. So I'm hoping that the audio is a little bit better then. Good. And we can always cut the first part of the live stream off. So, you know what? Let's switch to me, and then people can see me as well. Good. So, welcome. Yeah, no, I had it open. Like, ooh, I'm very windy indeed. Oh, damn, the audio was super quiet. But that's why you have this audio thing on YouTube, right? Like on the bottom, like there, you can just drag it, and I'm hoping that it's okay now. So if there's no further comments and people can see me and the audio is audible, then that's the way that we want it. All right. For viewers. Yay. Welcome. Welcome. So yeah, still a couple of minutes. 3 minutes, and then we can start. Say, yo, I was talking about the -20, right? So it was at -3, so everyone was running around panicking. The guy came, and turns out there's some kind of blockage. But if they can't solve it today, then they will come back tomorrow. And since tomorrow I'm one of the few people who are in the building, I'm probably going to have to let the guy in and use my magic keyring to show him through to our -8, our -20, not the -80. It's the -20. But yeah, I hope everything turns out okay. Like having freezer problems is one of the worst things that can happen to a molecular biology lab in that sense, because like everything's stored there, and it's uh, it's a problem when things don't work. Good. So, like you can see on the slide, today is going to be plots. So everything about plotting in R. Well, not everything. We're just going to discuss base plots. So that's part of the plotting thing in R, but like you also have ggplot and all kinds of other things. And I try to get in too much detail about packages, because there's like hundreds and hundreds of packages for R that have plotting functions as well. So they provide custom plots for plotting things on a chromosome or making three-dimensional plots, or but I don't think that that's too interesting, because in theory, if you need something like that in the future, you can always look up a package, right? That everyone has a computer when you're programming, so you can just Google kind of the type of plot that you want. But I wanted to more or less discuss kind of the basic R plot. So how do you start from an empty screen and build up so that you have a really nice nifty plot that you can use for publication. And do some basic stuff, right? Like how to add like the best fit line. So these kinds of things is what we're going to do today. There's a couple of other things that we are going to do, and that is I wanted to teach you a little bit about S3 objects, because like in the first lecture we had a question, why is R called R? And then I said because it's the successor to S. So okay, so the audio quality is perfectly fine compared to other YouTube videos. Yeah, I have that as well sometimes. I don't know why that is, because when I look at my audio meter, then it does say that I'm streaming at like a -10, -15 decibel, which is what YouTube actually advises you. But it might be that things like music and stuff um, is much louder. Like in the end, it's difficult to kind of make sure that the audio is perfect for everyone, but I hope it's good enough, and we'll see. So at least I think people can follow me. So it's two. So let's just start, right? So yeah, I told you guys we're gonna do plots, plots, plots. It's gonna be base plots. If you guys want to have a ggplot2 lecture, which is one of the most used plotting packages in R, then we can do that as well. I am not an expert on ggplot, but we have an expert on ggplot in our group, and she already prepared a lecture like 2 or 3 years ago, because people had, like I told you guys, we have an additional lecture at the end, or probably even 2 additional lectures depending on how the free days and holiday days and these kinds of things work. So that would be good to have a lecture about what you guys want to hear. So 2 years ago we did ggplot2, I think, and I'm not an expert, but I have a presentation ready for that. So that would be the easiest for me, of course, is that I don't have to prepare anything special, and I can just take the old lecture and do it for you guys again, and teach you guys about ggplot. All right, but some general remarks. Please attend the YouTube livestream. It just makes it more fun. And do throw things in chat, because that really helps for discoverability and all of these things. Same thing as like liking and like these kinds of things. I'm just asking you guys, but it really helps for discoverability. And ask questions as much as possible. Because if you are looking at a slide and you're thinking, oh, this is nice and I can probably understand this, but it would be good if there would be an example, then I can just make an example. So that's why I'm here, right? That's why we're doing this live, so that if you ask me for an example, I can give you one. And I put more assignments online if you want to practice more. So I've put them on Moodle. I will have to update my own website as well for the people that don't have access to Moodle. And of course, if you are running into any problems doing the assignments, send me an email. So, tidyverse, that's interesting. We didn't have that request first. So tidyverse. Could you send me an email? Then it's just there. So like, send an email, make the like suggestion for lecture. Then when we're like in July, we can see if we can do a lecture about that. But I actually never use tidyverse packages. I think I might have by accident, but generally the packages that I use come from Cron or they come from Bioconductor. So, but yeah, just shoot me an email, then I don't forget. I wrote it down, but I sometimes start a new to-do list and then it falls off. But yeah, like I said, so if you want to become a good programmer, right, and you want to learn how to program in R, you just have to do the assignments. There's no way else to learn programming. It's just by doing, right? Because you just have to get stuck on things, learn to recognize what certain error messages mean, and these kinds of things. So I put more assignments online. If you want to practice them, they're on Moodle. So they're all the way on the top, so above lecture number 1, called additional assignments. Again, if you have any issues, just send me an email. And if you are running out of assignments, then there's always like online sources. So one of the things that I found very helpful when I did my PhD is Project Euler. So Project Euler just has very general computer science questions that they start off with. And the nice thing is that you can just fill in the answer, and then they will tell you if your solution is correct. So they don't check your code or anything. It's just like this is the question, and then you fill in the answer in a box and you say check, and then they say, oh, your answer is correct, and then you know, okay, then probably my algorithm is correct as well. And that you can only become good at programming by practicing, and I can't stress that enough. Like I see a lot of people that want to learn how to program, and they are like, oh, and I followed like 5 different boot camps, and I watch all of the lectures online, and I you look at YouTube. But in the end, if you don't sit down with an empty Notepad++ window and start typing in code, then you will never learn in a way, because otherwise it doesn't stick. Programming is like 95% muscle memory. Um, Good. So with that out of the way, let's take a look at my answers for lecture number 4. And last week I did them all live. The week before I did them all live, and I don't mind. So if you guys want to do that again, that's perfectly fine. But I think it would be more efficient in a way that you guys ask me questions about the assignments. So I already got 1 or 2 questions via email, so I want to show those, and I'm going to program those. But for the other ones, I'm just going to show you my answers. And of course, if your answer is very different, then shout in chat, I had a completely different answer. And is my answer correct as well? Then we can just look at that. But I don't think it makes sense for me to sit here and type for an hour and a half. Um, Live, please. All right. All right, we can do that. We can do that. I don't have any issues with that. Because let me see. We have 56 slides. So 56 slides means that I'm going to talk for about 70 minutes. We have around 3 hours, I think, so should be perfect. All right, now we're just going to do them live, which is fine with me. So let me open up the R window as well. And let's start with assignment number 1. By the way, I'm not sure, will the exam evaluate mostly our coding abilities or our statistical knowledge? I have the impression that the focus is going to be on coding, right? Threefold. So there's going to be just basic questions that you can learn from lecture 1 and 2, right? Lecture 1 was a lot of history. So there might be a question like, who is the inventor of the Z-try, right? Which is just a basic knowledge question. There will be some programming questions, but of course, since you guys are doing it on paper, you can't write massive algorithms. So it's going to be more like, do you understand what's going on? So I will show you, for example, a piece of code, and there will be a question about the piece of code, saying like, what's the error here, or hey, what's going to be the answer if I do this? And there will be some statistical questions as well, right? Because we are a statistical course. So if I want to, or if I'm asking you guys, draw a normal distribution and draw a fat-tailed normal distribution on top, then you should be able to draw a normal distribution and know that a fat-tailed and a long-tailed distribution are different. So the focus is going to be on more or less all the 3. So there's going to be some warm-up questions. And in advance, I want to, well, not warn you guys, but there's going to be a drawing question, because I think that drawing is very important, and you can see that from my slides, right? And I like drawing, and I think that especially in biology, drawing trains you to look differently at things. Because if you look at a thing and you're not drawing it, then you're observing things differently. And for me as a biologist, or well, I'm a bioinformatician, but I studied biology as well. So for biology, it's very, very important that you can spot the odd things, because if you have a chicken population, for example, right? You're a chicken farmer, and you have thousands of chickens in a hole. Then you need to be able to spot the sick one, right? Because that's going to hurt your profit massively if you keep it in there. Or you need to be able to spot the mutant, right? The one which is slightly different than the rest. And drawing is very important in that because it teaches you to look more at the details of objects and not so much look at a concept, right? If you look at a chair, or if you imagine a chair, then you have a certain picture in your mind. But there's going to be a drawing question. Of course, you won't be rated on your drawing skills. It will be an additional question, which means that you can earn bonus points by making a nice drawing. And I'm going to rate drawings by the amount of little details and stuff that's in there. So you can see that like my drawing skills are also very minimal. But I like drawing and I think it's very important because it teaches you to look differently at things. So yeah, it's going to be threefold plus a drawing question. So all three things will be tested. So your ability to recall standard information that I gave you during the lectures, it's going to be statistics, and it's going to be coding. And so far, everyone that followed the lectures and more or less did the assignments passes the exam, because the exam is more or less testing if you paid attention and if you did the assignments. Good. So hope that answers your question, Davida. But don't worry about the exam. Like the exam is going to be easy. Well, not easy, but it's going to be doable. So if you're here and you're paying attention, the exam's not going to be an issue. All right, where's that window? There's that window. So question number 1, I think that we are going to use the iris data set, right, this time. So this is going to be answers to lecture 4, right? Because this is lecture 5. Yeah, answers to lecture 4. We don't need to set working directory. I do need a copyright statement. So copyright Denny Arends HU Berlin. All right, and I'm not going to add the date because that's not really necessary. So let me save it so that we get code highlighting. So answers 04.r, and I'm going to add live to it so that we can upload it later. Okay, so the first one is loading the data set. So that's fortunately easy because we can just say data iris, and then that will load in the iris data set. And then question number 1 was, so I'm just going to read it. The iris dataset contains 150 measurements of 4 phenotypes on 3 different species of iris flowers. Right, so imagine an iris flower. Can you draw an iris flower? If not, then might be the additional question this year. But the question here is question 1a. For each phenotype, calculate the mean, the median, and mode per species. So this is a really sneaky question because there is actually no mode function in R, at least not in base R that I know of. So the first thing that I did is write a function to compute the mode, because I need to do 3 different functions, right? And I want to have a function, because there's a function for mean, there's a function for median, but the mode is something that I think is not standard in R. So how do we do that? So let me just load the data set first and show you guys R. So data iris. And this is how the data set looks like. So let's look at the first 10 rows. Right, so we have the phenotypes and then we have the species. And for example, if we want to know the mode of the data, so the mode of the data is the number that occurs the most, right? So we need to take one column from the iris data set just to make a function. So I'm just going to call this x, just so that I can work with x. So the first thing that we need to know for calculating the mode is the unique, right? Because we need to know how many unique elements there are in X. So we know that we have 150 measurements. That was written down in the assignments. And there are around 30 unique measurements, right? So what we could do is just say, well, we are going to table the thing, right? And then it's kind of obvious what the mode is in this case. Right, because if I ask for the table, then you see that 5 is the number that occurs 10 times, while, for example, 6.3 occurs 9 times. So that would mean that the mode, in this case, is the number that occurs most often, which is the 5. So we can use the table function, right? But we need to figure out what is the maximum value in the table function. So we can do that because we can say max, right? So if we say max table, then it will say, well, the maximum is 10. right? And then I want to know which one this is. So I'm going to ask which table X is this the max of the table X? And then it will say 5, which is 8, but the 8 here is the index, right? Because it's the 8th number. Because I'm asking which, it will tell me which one. So the 8th number in the table is the one that occurs the most. And it fortunately gives me back the name of the number as well, which is 5. So we can just say names, and that's 5, right? So we checked it. So this is going to be our function. So I'm just going to copy this code, and I'm just going to go back to Notepad++ and show you guys. So I'm going to say that I have mode, which is a function. It works on X, and I'm actually going to call it my mode. And I'm just going to say, well, I'm just going to return this. And this should be able to calculate the mode. So the first step, right? Just a little bit of preparation, because there is no mode function. There might be in a package, right? So you could have Googled, you could have found that there is a statistics package which has a mode function, and that's perfectly fine. You can use that as well, right? Why do the function yourself if there's a package that does it for you? But I think it's easier to show you guys how I think about these things, right? So I just make a table. So a table lists which number occurs how often, get the maximum of the table because that's the one that we are interested in, and then use the which to figure out which of the table entries is the maximum entry, and then get the name because the name is the number that we are looking for. And we could put an as numeric around it, right? Because it's names, and we know that we're going to use it for numbers. So let's do an as numeric around it, just so that we make sure that we return a numeric value and not a character value. All right, so then the first thing that we're going to do is we're going to need to make some subsets, right? Because I have one table and it contains 3 species. But the question is, calculate the mean, the mode, and the median for each species. Right, so I'm just going to say, well, there are 3 species. The first one is Setosa, and I'm going to subset the iris dataset. And what do I want to subset? Well, I want to know, let me check if it's written with a capital or not. Yes, species is written with a capital. So I'm going to say species is Setosa. Setosa, I hope that that's not written. And I'm just going to check in R if this is going to give me only the Setosas. So seems to be the case. So, okay. And I want to get rid of the species column, right? Because like we're going to store it in a variable called Setosa. So there's no need for the last column. So that's column 1, 2, 3, 4, 5. So we're just going to dump the 5th column from the subset. And we can do that very easily by saying comma minus 5, right? Dump the last one. And this is then going to be Setosa. All right, so I'm just going to do that, and then I'm going to copy paste the code, and I'm going to go to Notepad, and I'm going to do 1, 2, 3, and I need to figure out what the other ones are. I think it's Virginica and versicolor. Yes, versicolor, not multicolor. So we are going to do versicolor, and then we are going to do Virginica, which is the 3rd species of iris. All right. So now we can start with doing the things that we want to calculate. Right. So hashtag 1a. So we want to apply to Setosa to the columns the function mean. Double point. We're going to want to do the same thing with the median. And then we want to use the mode, but this is called my mode because I wrote the function myself. All right, let's see if this works. Last one can go. Right, so I'm just going to put them all on one line because it's like quicker, or not quicker, but it's a little bit like, it keeps it a little bit compact. All right, oh, my mode not found. That's true, I didn't copy it in. So I'm just going to copy in the whole thing again, and all right, so here we see that so the first one is the means, second one is the medians, and then the modes. And here we see that sometimes we have 2 modes, which is perfectly fine, right? Because it can happen that 2 numbers are equally represented. So here the sepal length has two modes. So the first mode is 5.0, the second mode is 5.1, and the petal length is 1.4 and 1.5. So they occur equally often, right? And of course, if you have two numbers which occur at the same time, then the mode needs to return two numbers, which fortunately it does because of the which function. So we can just see. Good. And then we have to do this for all three species. So let's go back to Notepad++, and we're just going to go duplicate, duplicate, versicolor, 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 and Virginica, 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 and Virginica. Perfect. All right. Question number 1. That's it. Very easy. Make the subset, put it in a variable, and then just apply. Right? I told you guys that apply will make your life a lot easier instead of going with a for loop through all of the columns. Second question, or question 1b. For each phenotype, calculate the overall variation. All right. So that's on the whole data set, right? Not the one. So hashtag 1b. So I'm just going to say apply to iris to the columns, and I'm going to apply the overall variation. So I'm just going to say var, right, for the variation. And of course I have to remember, because the fifth column is the one that contains the species, I have to throw that away because I can't calculate the variance on a column which is not numeric. All right, so let's go to R. Let's see how that does. So we see here that the variance of sepal length is 0.6, sepal width 0.18, 3.1, and 0.58. Very good. And then for each phenotype, calculate the variance per species. So this is again doing the same thing as what we did before, right? So we're just going to apply, and I'm going to borrow it, so hashtag 1c. So I'm going to say apply to Setosa the variance, and I'm going to say variance, variance, and the other two species are called versicolor and Virginica. All right, so let's go to R, see what the variances are. Good, so we can see that the variance is highest in the Virginica, variance is lowest in the Setosa, and the versicolor seems to be a little bit in between. All right. 1D. Okay, create a function to calculate the geometric mean. All right, so geometric mean, let me think a little bit. That was the one where you multiply all of the numbers together and then divide by, no, not divide, then you take the square root. Let me see. I don't have the slides from last time open. So, oh yeah, so you do the nth root of all of the numbers multiplied together. So that's the one. So let me see, hashtag 1D. Right, so in this case, I'm not going to use variadic function. I'm just going to say harmonic mean is a function, which works on x. So x is going to be a list of numbers, right? And of course, if I start doing stuff inside of here, then of course I can check it easily. So I'm first going to write the harmonic mean. So I'm just going to say x is, I'm going to draw some numbers which I just think are interesting numbers. So something like this, right? And then we want to know what all of these numbers multiplied together are, right? So I'm going to say for I in x, right? So just have I be going through all of the numbers that are in x, and I'm going to say I have a prod, or product. Initially the product is 1, otherwise we can't multiply things together, because if I would say that the product is 0, then stuff multiplied with 0 is always going to be 0. So I'm just going to say product is product times I, not plus, but times I. And I'm going to use the is here, right? And I'm going to is, and I'm going to put a dot comma behind it so I can put this thing on one line, right? So if I would test this in R, then now I would assume that all of the numbers would be multiplied together, leading into a very big number. Product. So yeah, 2.3 times 10 to the 13th, which is a very big number, right? But we had some very big numbers in there. Of course, I could change x to make sure that I would know the answer, right? So if I would know 1, 2, 3, and 4, right? So 2 times 3 is 6, 6 times 4 is 12, 24, right? So this should lead to a product of 24. So let's just paste in the code again, and then I have product 24. Good. So it seems to work, right? And then I need to take the nth root. So the nth root is actually relatively easy, because that just means that because the nth root is something to the power of 1 divided by the root that you wanted to take. So I'm just going to say product to the power of 1 divided by the length of x, right? Because that's the number of numbers that we have, and I'm just going to add brackets just to be sure. This one should go first, but just to make sure that it divides the number first. And then this should be my function, and this is going to be my h mean, right? If I would store it, but I'm not going to store it. I'm just going to have R dump it to the screen. All right, so let's go back to R. Harmonic mean 6.8. Seemed reasonable in a way, right? Because all of the numbers are kind of lower than 6, and there's a couple which are much, much higher. Of course, I could take the example from the slide and make sure that it's correctly calculated. I think it's correct. So then what I'm going to do is I'm just going to delete x, right? Because something needs to be a function. So I'm just going to say copy paste. Let me give a little more space. So I'm just going to copy paste it in, and then I'm going to add space, 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 and I'm going to return this to the outside. And that's going to be my function. So that's my harmonic mean function. All right, next one. Geometric mean, right? So geo mean is a function, again, works by x, and this time I'm going to cheat a little bit, or not so much cheat, right? Because the harmonic mean is defined as the number of numbers divided by the sum of 1 divided by the numbers, right? And one of the nice things is that R is a language which has built-in support for functions. So if we go to R, right, and I have here my x, which is still stored. So I just want to do 1 divided by x, right? And fortunately, R understands this and just does so 1 divided by 1, 1 divided by 3, and so forth, right? So this is going to be 1 divided by x, and then I need to take the sum of all these numbers. There's a built-in sum function that I can use, and then it's going to be the length, so the number of numbers in x divided by the sum of 1 divided by x. So this is just going to be my function. So we go to Notepad, and I'm just going to chuck this into the geomean, and this is going to be my geometric mean, and of course I want to return this to the outside. All right, geometric mean function, which is 1e. Just as a tip, right, this whole product thing is completely unnecessary. Besides the sum function, you'll set the prot function, so this could have just been written as prot of x, and that would be good as well, right? No problem, because it's a built-in function. Of course, you can sum numbers together, but you can also multiply numbers together, which is the same thing. Alrighty, good. So first plot in R. Use the histogram function, look up the help file, and for each of the 3 iris species, create a histogram for the petal length column. All right, good. Create a histogram for the petal length column. Okay. Hashtag number 2. So fortunately, I already did the subsets, right? So I can just say setosa, take the petal.length, I think, petal length, and do a histogram of this one. And then I'm just gonna doop. Nope, one too many. We're going to do versicolor. We're going to do the exact same thing, and then we're going to do Virginia, also the exact same thing. So I want to show all of the 3 together, right? So I'm just going to say op par mf row is C. I want 1 row, 3 columns, so that I can plot 3 next to each other. Go to R. This is what you're going to learn today, but you could have looked in the help file. In the end, it doesn't really matter if you just made 3 of them differently, but it's nicer to see the things next to each other, right? Of course, these are not very good plots, but that's what we're going to learn today, because we want to change like the thing here, and we want to make sure that the x actually says that this is the petal length in centimeters, and the frequency. But this is the basics of creating histogram, right? Just call the hist function with the thing that you want. Actually, there's an error. I see here now that it's twice versicolor. So I have to change that and make sure that the last one is not the versicolor, but the Virginica. And add the error here as well. So Virginica, 3 species. Let's go to R, make sure that we update it. You could have seen it because the 2 histograms were the same in the end. Okay, that's 2A, and then 2B. So the question is oh, you can actually show them all in one as well. So instead of doing this oppar mfrow thingy, what we could have done is, I think you can add them. So you can just say add equals true. And here you could say add equals true. Then we have to, of course, give them colors, right? So if I want to make one plot, then I'm going to call the histogram. And I should first compute what the range is, because otherwise, because based on the range of the first one, it will make the window of the plot. And then if I try to add the other one in, but the other one has a much wider range of data, then some of the data points will fall out. But just to show you guys that you can add them, I'm going to say color is red. This one color is blue. And then the first one is going to be color is orange. All right. And I think this works. I think that instead of showing all 3 of them, right, and now we already see the issue, because if I use Setosa, right, which is from 1 to 1.8, if I would add the histogram of versicolor, you would not see it because it only starts at 3. And the Virginica starts at 4.5, so they are very different. So in this case, you can see that you can only see the first one. The other 2 are more or less outside of the window. Of course, we can change that by just saying I'm going to set up my own plot window. And I think we already discussed this. So I can just say, let's look at the graph. So the maximum frequency is like 12. So I'm going to say plot x equals c 0 to around 6, right? Because that's kind of the maximum petal length. Y equals c 0 to 20, no idea. Type equals none, don't plot anything. And then I have to add this one to the plot as well. And now we should be able to see all 3 of the distributions in one go. Let me close the window so it opens up a new one. And now we can see here that it puts all 3 of them in one thing. Of course, you can see that this is, of course, a very, very poor comparison, because like the width of the histogram here is much smaller than the width of the histogram here. But that has to do because the histogram function tries to figure out what the best way of visualizing is, and it doesn't know that I'm going to add 2 more later. But I could set the breaks myself. But I don't think that that's the good solution, right? The best solution would be is to just say, well, we're just going to plot them all, and we're going to use 3 plots next to each other to make sure that we can show them and compare them. So I don't think that this is a very good plot, so I like this one much more. Alright, next one. Use the par function to change the size of the main title to letter size 2. Alright, so changing the letter size is just, it's the letter size of the main title. Okay, so this was just for you guys to force you guys to go through the help file of par. So let me open up the help file of par quickly, because it's a big help file, right? So you can do this in R by just doing $par. So look at all of the parameters. Then I have to move this to the Firefox window that I actually opened for you guys, and then we look here. Right, so you can see that this is a massive help file. There's like all kinds of parameters that you can set. It has some images about how you can set the outer margins. There's the inner margins. There's the mfrow if you want to do more plots next to each other. Here they have the OMA, which is the outer margin when you do multiple plots. PCH, PTI, so hey, it's all explained, and it's just a big help file. But the idea is that you guys would have to look in the help file and see what it is. And of course, you can have examples, which is the good thing about R, is that any function in R comes with built-in examples, which would be very good, because you can just copy paste in the examples, see what happens, change a little bit, and then figure out. All right, so let's go back to Notepad. So in this case, I already forgot what we were trying to do. We were trying to use letter size 2 for the title. All right, so I'm going to say op par, and I'm going to say cx.main is 2, because that's the proper parameter that we want to set. And then just let's make one histogram, right? And let's make one histogram before we do this. Just so that you guys can see the difference, and I want to have them next to each other. So I want to have one row, two plots, and then I want to have petal length of setosa, petal length of setosa, and in the meantime I'm going to change the cx.main, so I'm going to make the magnification of the main bigger. Alright, so let's go to R, and then this is how it looks like. Right, so this one is already quite big, but here you can see that it's even bigger and it starts falling out of the window. It's just for you guys to read the par help file, which is like one of these main parameter or plotting parameter help files. All right, use the par and parameter mfrow to create 3 subplots in a single window. Okay, so that's actually what we already did. Make sure each subplot has the header of the species. Okay, so that's not exactly what we did. So what I did with 2a was actually 2c already. Right, because we already know that you need to use op par. Where does cx main stand for? So main stands for the main title, so the title of the thing, and cx stands for magnification. I don't know what cex stands for, but that's a tricky question. Might be in the help file, but it's just something that you have to learn. It's magnification, so you would say mag.main. But in R, like anything is and in a way, to me it makes sense, but that might just be because I'm used to it. So, but yeah, good question. Let me see in the help file. Might actually be in the help file where CX stands for. Nope, doesn't explain it. It just says a numerical value giving the amount by which the plotting text and symbols should be magnified relative to the default. This starts at 1 when the device is opened and is reset when the layout is changed. Note that they have arguments, so no idea, just randomly chosen. And I'm quite used to it. If I think about like magnification, I always think, oh, that's CEX, but in a way. But in this case, you just open the help file, right? So if you look at the help file, then in this case you would have, because it would say use par to change the size of the main title to letter size 2. Yeah, okay, it might have mentioned the word magnification, right? Because then you could have just searched for magnification and find it. But you also can do the magnification of the axis, magnification of the other labels, and so you can change all of the different magnifications if you want to. But where does it stand? It's just a parameter name. So no idea who came up with why it should be CEX. It's a good question, actually. If I figure it out, I will let you guys know. So question 2a is actually question 2c, because here we ask the question. So this is 2b. And 2c is the same question as we had before, because here I just wanted you guys to make... Yeah, okay, I just wanted to make you guys a histogram for the 2 species, or for the 3 species, without having them into the same plot window. But here we actually have, so the question here is use the par and the parameter mfrow to create 3 plots in a single plot window holding the petal length of each of the species. Make sure each subplot has a header with the name of the species. So in this case we want to add a header, right? So a header is called main, and here we're just going to say, well, this is Setosa. And then we are going to say for the next one, this is versicolor and virginica, just to get rid of the ugly names that we had, right? Because the names look relatively ugly when you just do the plot like this. So let me show you how ugly it looks when you just do the standard plot, right? Then you see that it says histogram off, and then it mentions the whole thing that you put in. But of course we want to just have the names of the species, because the other information is completely overkill, right? We can see that it's histogram, so why would it be in the title? But now we see that it looks like this. And of course the magnification stays, right? So I think it's still magnified by 2. And then if I would do this again, and then I would, and I would do the plot again. Yeah, so it's already at 2 magnification. But now we have the setosa here. We could change the x-axis as well, right? Because here we still see setosa petal length. And of course here it should just say petal length and then have the unit in brackets, right? Petal length in centimeters or millimeters. Good, good, good. Save the plot from 2B to a PNG file. All right, from 2B. That's weird. Why would you save the one from 2B? I'm going to save the one from 2C, since we already have that, right? So I'm going to say hashtag 2D, and I'm just going to say PNG, and I'm going to do this, and I'm going to shut off my device. And here I also use like additional layout. And this of course is not entirely correct because I'm not opening a block, right? And I need to come up with a name, so I'm just going to say my plot.png. And then I could say width is 1024, height is 768, right? So just make it the width and height of a standard monitor. And then this would be able to save the file to my hard drive. Of course I can't really show you guys that because like if I paste this in R, it will not do anything. I can actually shut off the standard device as well. But I can show you guys because when I say dir, then that's a bunch of files where I'm currently working. But one of these files should be called myplot1.png. But I have no idea where I am actually. Oh, I'm in my documents. So that's just a kind of massive folder with all kinds of stuff. So it even has my WhatsApp backup folder here. Anyway, doesn't matter. So you just use the PNG, then you do the plot, and then you do def off, and def off writes it to the hard drive. And everything in between is just executed line by line. Alright, 3a. Create a single plot showing 3 box plots next to each other comparing the sepal lengths between the different species. Use the axis function to add human readable axis to the plot. Okay, so now we want to make 3 box plots, right? And we want to compare the sepal length between the different species. So here we can do a little trick because we can use a function. So in R there's a special way to write down functions, which is using the tilde symbol. So if we look at question number 3, then in this case we can say iris, the whole data set, and I want to plot the sepal length. So let's just do that. So we take the sepal length of iris, and now I want to know the sepal length of iris conditional on the species, right? So this just means define a function where you take the first part and then kind of regress it or split it out by using the second part. And we will get back to this because when we start doing linear regression and other like statistical models, then the tilde function will come back a lot. And in this case we want to separate out by the column species. And that's it. And of course we want to make a box plot, right? So we can just say box plot this, and then this should be showing us what we want to show. Oh, wrong click. All right, and then here we see the thing. And fortunately for us, like it already made the axis properly, because you weren't supposed to know this thing, right? So you weren't supposed to know about the tilde operator yet. So for you guys it would have been more difficult. So how would you normally have solved it if you would not have known about the tilde operator? Well, then of course you would have needed to set up your own plot. So in this case, setting up your own plot. So doing it with the knowledge that you were taught. Right, so I first have to, for a box plot, I need to know what the maximum value and what the minimum value is, right? Because I need to know a y-axis, right? I need to know where do I need to start the y-axis and where do I need to end. So I can say something like y range is a combination of iris, so the minimum value of the sepal length, with the maximum value of the sepal length. Right, so I'm just going to make a little list with two elements. First element is going to be the minimum, other element is going to be the maximum. And I'm going to do a little trick, because if I take the maximum right, then the maximum value will be kind of on the top of the plot, but halfway out of it, because it's a circle generally. So I'm just going to say, well, give a little bit more space, right? So I'm just going to say take 15% extra compared to the maximum, just so that we have some extra space on the top of the plot. The X range is pretty easy. So the X range is like 1, 2, and 3, right? Because I have 3 species, so I need to have 3 different things. So I'm just going to make my own plot. So I'm going to say plot X is C 0, 3, right? And then I'm going to say Y is Y range, and I'm going to say type is none, right? So just make an empty plot. So how would this look in R? So in R, I would just make an empty plot like this. And now you can see that it plots the x-axis, which I don't want. So let's disable plotting of the x-axis and also disable plotting of these, right? Because here it says this and here it says y range. But I want to have good names because I want to have a good plot, and I want to make it look a little bit more beautiful. Right, so I'm going to say plot x-act is none. So don't do an x-axis. LAS is 2. I will explain why I'm going to do that. And I'm going to say xlap is species, right? Because that's going to be on the x-axis, and ylap is going to be sepal length, and that is probably measured in things like centimeters, right? So just make the plot a little bit better looking. So now if we go and we do this, then we see now that here we don't have an x-axis, and it actually flipped the numbers here around so that they are readable. Here we have a thing, and here we have so we have the proper x and y labels. I could have given it a main, right? So I could have given it a main is something like Q3A, right? For question 3A. All right, so now I have my empty plot, and I can just add the box plots to it. Right, so how I'm going to add the box plots to it. So let's go back to Notepad. Of course, I'm going to use the box plot function. So I'm going to say box plot at is 1. So at 1, plot a box plot, and what should it have? Well, it should have the sepal length of setosa. So I'm just going to say sepal length setosa, and I'm just going to do it like this. And of course, I have to say add equals true, right? And I can say color is orange, just to make it look a little bit better. Alright, so let's see if that works. So we go back to R, we plot it in, and then we see here that at 1, something's going wrong here. Plot. Okay, yeah, the box plot is starting to override some, because it tries to make its own y-axis, so that's why we now have the numbers twice. So I have to say in the box plot that I don't want to have a y-axis, so y-act is none. And now if I do the plot and then I do the y-axis, then now it should be okay. Right, so now we have the numbers back and not the numbers twice. Alright, so let's copy it and go back to Notepad. So this is the first box plot that we're going to do. I'm just going to say Ctrl-D for duplication. So at 2 and at 3, I want to plot the versicolor, and I want to plot the Virginica. So setosa is going to be orange, versicolor is going to be versicolor, which is red, and then this one's going to be hot pink. Why not? Feeling generous today, so let's do a hot pink plot. Alright, go to R, and then we see it. Alright, so now we see something strange happening, right? Because this box plot falls out. And this has to do, let me actually go to the plot and do not disable the x-axis, right? So you can see what's happening. Because I'm saying that I go from 0 to 3, right? And I plot the last one at 3, part of the box plot, because the box plot has a width, right? So part of it falls out. So in this case, I could have better started from like 0.5 to 3.5, right? Because then I have a little bit of white space before the first box plot, and then I would have a little bit of white space before the second box plot, after the last box plot. Good, so let's do that. So instead of going from 0 to 3, I go from 0.5 to 3.5 so that the box plots are more or less centered, or should be centered. And then it looks like this. So there's one outlier here in this one. Don't know which one this is, but I have to still add the axis. So let's add the axis with the proper name. So I can say axis. So I want to plot on the first axis, because first axis is the x, second axis is the y. Then we have the z-axis on the other side, and then on the top we have the fourth axis. So at the first axis at 1, 2, 3, I want to do the following names. So I want to do setosa. Then the next one is versicolor, and the last one is virginica. Alright, that should give me my axis. Let's go to R. Right, so now we don't have an X, and we now are going to add our own custom X. And of course I need to fix this to make sure that we have a capital there as well. And of course I could give them the colors as well, right? I could just say color is, and then I'm going to say orange, red, and hot pink. Right, so I can also use colors in the axis if I wanted to, just to make the plot look a little bit nicer. Unexpected comma. So an unexpected comma means, this is a very common error, right? So it means that I probably forgot to close either one of these brackets, or there is a, yeah, so here you see col is round bracket open, right? So there's a C missing here. So why does it say unexpected comma? Well, it doesn't expect a comma here, because I'm not using the combine function, right? So here I'm just saying this is a bracket system with 3 characters in there, but I'm not telling R what to do with it. So it parses this expression, and up until orange everything is fine, right? Because color can be orange, but then you have a comma and it doesn't expect this one, because I forgot to open up the to call the combine function. So I just have to add the C here for the combine function. Right, and these are things that you only learn by typing in your own code, right? Only then do you run into these issues. You stare at your code for a while and you're thinking like, why is it not expecting a comma? But then you notice that you're missing it. Yeah, the color doesn't look too good. It just colors the axis itself, but looks kind of okay. We could have added a legend as well if we wanted to, and in this case, the 1.5 or the 15% extra space on the top was not really necessary, because that it's just too much. But you live, you learn. Good, so that was question 3a. Let me look at question 3b. So question 3b, use the notch parameter. What can you say about the differences in the observed sepal length? Alright, so let's use the notch parameter. So I'm just gonna copy paste the whole thing, and just gonna delete this one, because this is the easy way, right? So this is just let R do the whole computation, saying that I want to do sepal length, look at the different species, group them together, and you make the box plot. But in this case we just want to say comma notch is true, and we also want to do that for the second one and for the third one, and then just plot it in. So let's add the notches. So what can we say? Well, we can say that there's definitely a massive difference, or there's a significant difference between the sepal lengths of these different species. And we can say that Setosa is the smallest one with an average of 5. Then we have versicolor, which has kind of an average or a median of like 6. And then there's Virginica, which has a median of like 6.5. And if I would draw a line from here to here, I see that they don't overlap. So there is a significant difference between the 3 different species when we look at the sepal length. So that's the conclusion in 3b, right? What can you say about the differences? So the differences are significantly different between the 3 different species. Peter, goedendag. Alright, so that's it. If you have time left, please work on the previous assignments or start reading the free Beginner's Guide to R book, or do some additional assignments from the extra practice.pdf. So, could you explain the notch? Yeah, so notches are based on the fact that in in a box plot, we look at the range, right? So we see the medians, we see the quantiles, but the notch here is based on the sample size. So the more samples you have, the smaller the notch. So it's kind of a graphical representation of the amount of samples that you have. And when two of them overlap, let me see, there might be we have petal, sepal, what were the other? Let me see, iris 1 to 10. Let's look at the petal length, right? Let's hope that, petal width. Let's hope that some of them don't overlap, or that some of them do overlap. So I'm just gonna change sepal by petal. So I'm gonna say petal, 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 and petal length, and update it here. Oh, you guys can see that. I just changed every sepal with petal, just to look at one of the other phenotypes. And I'm hoping that one of those don't overlap. Yeah, no, those also don't look good. These look even worse. So here there's no overlap. But when they are hitting each other, then there is no significant difference. But if they're different, then there sure as hell is going to be a significant difference. So the notches are kind of based on the standard error. So it represents kind of the standard error around the median. And we know that if two standard errors overlap, then the chances of this being a significant difference is very low. But if they don't overlap, then there almost definitely is going to be a significant difference, because and why are the upper and lower half sometimes not the same same size? I thought the median divides the data into two halves. Oh, you mean these ones? Yeah. So this is the median, and this is the so these are the quantiles and these are the quantiles, but it hides how many values there are. Right? What we could do to make it more clear, right, is to add in the data points. So if we do a single box plot, so let me give you an example for that, because it's a little bit sneaky, right? Because you don't know how many values there are in the quantiles. So let's just do one box plot, right? So let's take the setosa and the petal length and notch it, and just don't add it to the plot, but make its own plot. So let me guys show you Notepad. So I just took one, just take the petal length, take it out. We go to R and we make the box plot. Right, so the question is well, here it looks to be more or less in the middle. Right, we see that there's one outlier. So let's take another one. Let's take the Virginica. Right, so here you see that the standard error on the top is higher, or seems to be higher than the quantiles on the bottom. So the reason is that there's just as much numbers here as there are here. It's just that these ones are more or closer together. So I can visualize that, right? So I can just say points. The x position of the points is a repeat of one length of n row of Virginica, and then the points that I want to plot are just the petal lengths, and I'm going to plot them not all at 1, but I'm going to plot them at 1.2. Right, so I'm going to put them slightly next to here, and every value, the x position of every value is going to be here, and I'm just going to plot the individual petal lengths next to it. Right, so now we're just going to count. So you can say that below the median there's 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. Above the median there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And now you're thinking, why, you're screwing us over. There's like more numbers on the top than there are on the bottom. So that's not the median. But there actually is. And that is because some of these points are overlapping each other, and you can't see them overlapping. So how can I solve that? So let me plot it again. So now instead of plotting them all at 1.2, I'm actually going to plot them at 1.2 plus runif n row Virginica. So I'm just going to add a little bit of randomness to it. Right, and the randomness that I'm going to add is between minus 0.1 and positive 0.1. X and Y are length different, so let me see. Oh yeah, I can't use the repeat function then. So let me just not use the repeat function. So I'm just going to draw some random numbers, and that's going to be from 1.1 to 1.2. And then there's an unexpected comma. I'm just trying to mess the code a little bit, but let me show you guys. All right, so now here we see all of the measurements. Let me move them a little bit more. So let's do the box plot again, and then instead of 1.2, let's use 1.3 to 1.4. Right, so here we see the real measurement values on the side. And of course, sometimes they still overlap, but now you can see that they are more or less, that the median actually divides the same numbers on the lower half as there are on the upper half. And you can use this like little trick where you say, okay, so instead of plotting them all on one line, I'm just using a little bit of random. So that's why the random numbers are so cool, because random numbers can help you make these kinds of plots. So yeah, no worries. That was the question. Good. And we actually finished exactly on time because there's no more assignments. So perfect. Are there any more questions about the assignments? Because this time they were actually relatively quick. Like last week, we actually spent much more time on the assignments. But yeah, no, you're welcome. Thank you for the question. That questions are always welcome because that means that you guys are paying attention. And I'm not talking to myself in my office, which some of my colleagues are thinking that I'm doing, which is perfectly fine. But I'm not. I'm talking to you guys. So, all right. Anyway, so those were my answers for lecture number 4. I will upload them. Can Anna do a gift break from Oscar? Unfortunately not. I already prepared the gift breaks. Yes, this is Peter Arends, of course. That's I thought that was clear from the name. Like Are you uploading the code you've just written? Yeah, I'm uploading the code that I've just written, and I'm uploading the official answers, which of course are not the official answers because like it's something that like I do, right? So I generally program them in like once in a while. All right, so plots for the rest of the day. But first, since it's 3, we are going to take a break. And the first break is going to be, and I have to think hard, creepy crawlers. It's going to be insects. I hope we didn't have that one yet, because I'm not going like in the alphabet. I just have a big folder with all kinds of different animated gifs. But we are going to do insects today, I think, for break number 1. And otherwise it's break number 2, because I'm quite sure that I put insects in. So enjoy the animated GIFs, and I will start in some music, and then we will also switch the scene. So let me start in the music. The music of today is called funk. I just use my copyright free music from my Stream Deck so that I don't get into issues. But it's going to be funk, and then you guys are able to watch the insects. I first have to actually turn on the sound, then turn on the music. That seems to be okay. All right, and then we are going to the break. So I will see you guys in 10 minutes at 3:12. All right, bis gleich. I almost made it. I almost made it. All right, welcome back. Part number 2. Plots, plots, plots. So if we're quick, actually, we don't get another break because I have 52 slides for you guys today. But if you want any examples, just say so and I can do an example for you guys because we have enough time. Good. So, don't click anywhere, click there. Okay, so this is going to be the overview of today. For today I want to explain to you what S3 and S4 objects are and how they relate to plots. Because you can create custom objects, right? We saw that with the class function you can figure out what the class of an object is, but you can also use it to create your own classes. And this is very useful, especially when you're writing code for other people. Then hey, you can have a function which, for example, reads in 2 or 3 files, puts it into an object, and then give it a custom object name. And then we will talk about custom plots. So we already did a couple, right? But I want to talk more about points, the function, how you can use it. I want to talk a little bit about scatter plots, about chromosome plots, about circles, about different color schemes that you can use. And I also want to talk about violin plots. I added that in relationship to last year because we saw box plots, right? And box plots give you an general idea how the data looks like, but a box plot kind of assumes that your data is a normal distribution. That's why it shows you the median and the quantiles. But violin plots are much nicer when you want to show distributions. So it gives you a better overview of how your data looks like. And they generally look better in publications as well. Good. So in R, you have objects. And these objects in R are not R objects, they are called S language objects. And we can use this to set a custom class for an object, right? And we can use this then to define common functions that people can use. So in R, you have, for example, the summary function, you have the print function, and you have the plot function. But these functions come with something behind the dot, right? So if I call summary, what the summary function first does, it looks what the class of your object is and then calls the corresponding summary dot and then the main class of your object function. So you can overwrite or you can make new functions that do that. So when R knows the class of your function or of your object, then it also can figure out which function it needs to call. So let's create a very simple object, right? So here we're creating an object. So I'm saying my object is a list, and this is a list which has 2 elements. The first element is called CHR for chromosomes, since we're in a biology department. In this case, chromosome is a vector, and it has 2 elements in there. So the first element has the name 1, and that's 15. The second element is called 2, and this has the number 10. And then the second object in the list is called genotypes, and this is a matrix. So I have a list, and the first element of the list is just a basic vector, and the second element of the list is a matrix, a big matrix. In this case, 10 rows, 25 columns, and 250 entries. And what I can do is then when I make this object in R, I can set the class. So in this case, I want the class of my object to be list because it was a list. So I don't want to destroy the fact that it is a list, but I'm going to give it a secondary class. So I'm going to add the class my class to the object. So now when I type in R my object, it will roll everything down the screen. So it will show me that this is a list, right? And it's a list which is a named list. So the first element of the list is called CHR, and then CHR is a vector, 2 elements. And then we have the second element of the list, which is called genotypes. And this I shortened down because there's like 10 rows. And then on the bottom, when you type this, you see attribute class, 1 list my class, right? So we just updated kind of this hidden state of the object, and instead of a list, it's now a list, but also a my class object. And of course you can come up with any name that you want. So for example, if I would do genotype matrices, then I could say that the class of my object is genotype matrix. So now we can define custom functions. So now I can, instead of when people type my object in R and having like hundreds and hundreds of lines of data run through the screen, I can just make a summary for people. So how do I do that? I just define a custom print function. So I say print.myClass is a function, and this is always how the function should look like. So the X here, this is the object which has the class that we define. So X is an object which has as a class my class. And then we do comma dot dot dot, and the dot dot dots here are not used because I don't want people to have multiple parameters. But you could if you wanted to. So, and then the summary that I want to give is very basic. So I want to say cut my class object, and then I'm going to say content double point is the sum of the chromosome vector. That is the first element of the list. And then I'm going to say these are the number of markers, for example. And then I'm going to say content is n row x genotypes individuals, right? So I'm going to just imagine that this object which I created has 25 markers in this case, so 25 columns in the matrix, and every row in the matrix is an individual or an observation. So now when someone types my object in R, this is what they get back. So instead of having hundreds and hundreds of lines of the stuff which is inside of the object run through the screen, it will give me a very short and concise summary. So it will just say, this is a my class object, it has 25 markers and 10 individuals. So this is really useful because it produces a lot less spammy output, right? You can imagine that if I have a matrix which has 10,000 rows, then this will just continuously roll across the screen for like a minute or two, showing me all of the numbers, but I'm not really interested in the numbers, right? So it's one of these ways that you can make an object which, when people type the name of the object, they don't see exactly what's inside, but you abstract that away and you just give a very short summary. And one of the nice things about using this is that you can also perform basic checks and you can issue warnings. So you can say, well, oh, this object is not good. What is the difference between X dollar genotypes and X genotypes? It's not. There's no difference. They're both the same in this case. You can use the same thing for matrices. So you can say if you have a matrix, then you can say dollar and then the name of the column that you want to select. But in this case, we have a list and a named list. So in this case, we normally would have used X double square bracket, and then we would say 2 for the second element of the list, and then we double square bracket close it. But dealing with list, it's just easier to use the dollar. So the dollar just means from X select chromosome, from X select genotypes. And if it's a list, it selects it from the list, and if it's a matrix, then it assumes that this is the column name. So it's the same thing, it's just written down slightly differently. And sometimes you want to use the one format, and sometimes you use the other format. But good question. In the assignments, I had an error with brackets, but with dollar it worked. If you had an error with brackets, then you probably had to use 2 brackets. Because the 2 bracket thing is for list, right? So everything is a single square bracket if you have a vector or a matrix or a data frame. Only when you use a list, you should use the double square brackets. Because that's just how R works. The list is a little bit special because you can put anything in, even a matrix or another list. So generally objects or custom objects in R are lists with several elements in there. Yeah, so if you use 1 and you get an error because it can't find the object, then just try the double square bracket. And that's because of the listing. And lists in R are a little bit different than all of the other objects because they are the basis for this kind of overloading, right? This is what the official name for this is. Here I'm overloading the print function. So I have in R, there's literally like hundreds of different print functions. There's a print function for a vector, there's a print function for a matrix, there's a print function for data frames, print function for functions, variables, and you can overload the print function and you can make a new function which is called for a very specific object. So of course we can also overload the plot function, right? If I would just call plot my object, then R doesn't know how to plot this thing. right? Because it's a list which has two elements. The first thing is named CHR, the second one is named genotypes, and it does not know what to do with it, right? So it just throws an error saying, don't know how to, cannot coerce to, right? And then it just says, I'm giving up, I have no plot function that works on this object. So of course we can define our own plot function saying plot.myClass is a function which again takes x as an input and then comma dot dot dot. And in this case we want to use the dots, right? Because we want people to be able to pass additional parameters like the color of the plot that they want to use, or the main, or the X label, or the magnification, or the other things. So I very basically like do a little trick. So I say I have a plot function and I'm just going to call image on my genotype matrix. And then I'm going to pass all of the parameters that the user gave into the image function. So now that means that this plot.myClass function supports all of the parameters which the image function supports as well. And then I'm going to do box because I want to have this nice box around it, because otherwise it will only plot the x and the y-axis, but I also want to plot the other two axes. So I also want to plot the z-axis and the w-axis, so the ones on top. And now if I call plot my object, then it calls this custom plot function and it shows this plot. So you can prevent users from knowing what's exactly how your object is structured, but you can still give them all kinds of different plot functions to work with. The same thing is for image, right? If I would call image of my object, the image function cannot deal with lists, but I can overload it, and I can say image my class. Again, the same thing, just plot the genotype matrix using the image function. And now when I call image my object, I get the exact same picture. Good. So that's overloading, which is really useful, especially when you're writing code for other people and you need a lot of different things, right? For example, if I'm thinking about DNA sequencing, then I need a reference genome. I need to know all of the genes. I need to know, for example, the sequence reads that I have. I need to know where these are mapping, what the quality is. So I can hide this all into one single object, which is created and having a create my object function, which then when you call it, it loads in all of the different files that it needs, makes one list with all of these elements in there, and then it has these custom print and plot functions so that when people call plot of the object, they get a really nice overview of where, for example, the reads are. And of course, this is not beholden to biology. Also, when you do like political sciences, or when you do like mathematics, or when you do economics, hey, you can think about having multiple companies and having different measurements on these companies, and that you, instead of want to roll hundreds and hundreds of lines of statistical data from a company across the screen, you might just want to have a very short summary saying that this object contains 10 companies, the minimum amount of employees is 10 and the maximum amount of employees is 100, right? So you can do these kinds of things. And then when you would think of a plot function, it could make, for example, box plots of each of the companies. Good. So that's the idea behind S3 and S4 objects. S4 objects are a little bit more complex because they can come with their own functions as well. So not plot and print, but I think that you would get the idea from how this works, right? So you can just define a new function name, plot dot, and then an extension, and then this extension is matched with the object that you assign using the class function. So in R, when you make a plot, the philosophy behind this is called the artist palette model. So the idea is that you start with a blank canvas, right? An empty plot. And then you just start adding things to it. And so you start with a plot function, or you start with an image function to make an empty plot. And then you use the different drawing methods or annotations to add and modify this. And this works from the back to the front, like you're painting, right? You paint the background blue, and then you wait a little bit for it to dry, and then you paint the sea in a different color of blue, and then you paint the beach in another different color of blue. It's like how Bob Ross did his paintings, right? So from the back to the front. And this is how the R-based plot philosophy works. And this is called artist palette model. You have other models for making plots, but this is how base R works. So I like this a lot. I think it's very convenient. It mirrors how many people think of how you should build up plots and, for example, analyze data. Right? Because when I want to have a custom plot of my data, the first thing that I do is I make a little drawing. Right? So I just take a piece of paper, I draw an x-axis, a y-axis, and I just make a plot, and then I start adding elements to the plot. And the way that I add the elements to the plot is the way that I'm going to write my plot function. This is the way that I'm going to build up my plot, right? So there is some drawbacks to this philosophy, right? Once you start a plot, you cannot easily go back. You have to start all over, right? So if you have hundreds of lines of code which create your plot, and on the 80th line of code you figure out, oh, I should have made the margins different, you have to start all over again, right? So you have to kind of close the plotting window and then start issuing the commands one by one, first setting the margins, right? Because that's the first thing that you need to do, because even when you make an empty plot, you need to know how much space you want around it. So you need to plan in advance. And there's another problem, because it's difficult to translate to other formats or outputs once a new plot has been created. It is not a graphical language. And one of these things that you can see that from is from the PNG file that we did during assignments number 4. Because if I do a plot in R, it can look really nice in R, but then when I try to do the exact same code, plot it to a PNG, it might look very different, because the PNG might be differently scaled or might use a different point size. So that is why when you make a plot in R and it looks really good in R, just writing PNG and def off around it will not always work. But in the end, a plot is just a series of R commands, so you just have to fiddle with the fact that in PNG the point size might be slightly different than, for example, in a JPEG, and that might have, again, a slightly different margin than when you are making an SVG or scalable vector graphics. So it's not easy to go from one medium to the other, right? The standard R plot window is one medium, PNGs are another medium. So you might have to adjust the code a little bit, saying that, well, I want to scale some things down and other things need to be scaled up a little bit. But there is a difficulty to translate. But all in all, I'm a very big fan of base R and about the philosophy, because it allows me to make any kinds of plot that I imagine, because if I can draw it, I can also make the computer draw it in the exact same way. Just following the steps that I do on paper, I just have to tell the computer, okay, I draw a circle, so you draw a circle. I draw a square, so you draw a square, right? So it's a one-to-one relationship with how I would draw an image compared to how I would make a plot. Good, so I want to show you a very small example. I've updated the example a little bit compared to last time, just to remove some of the bugs, and I've made new plots for you guys. And here I want to also introduce you the width function, because the width function is really, really useful. So here I load the library data sets, because I'm going to use the cars data set. So the cars data set is a data set which has, for a lot of different cars, it has things like the speed at which the car can travel, the total distance that it can travel on a single tank of gas, it has the gas usage in miles per gallon and these kinds of things. But here I'm going to do a little trick, right? So I'm going to say with cars, so with this data set, plot the speed and the distance. So what happens, because I do not have a variable called speed and I do not have a variable called dist, right? But because I'm using width, everything in the second part of the width function assumes that the variables that are mentioned are columns of the cars data set. And this is actually the reason why read table converts your column names into proper variable names, right? So when I say read table and I have a column name which starts with a letter, with a number, then it actually puts the letter X in front of it, because a variable cannot be named 5 as a number. So, but it can be called x5. So that is why this check names is false or check names is true. Either kind of eats up your names or the names are perfectly fine. So that's why the with function is there, because you can very easily shrink your code. Because otherwise I had to say plot cars dollar speed cars dollar distance. And especially if I'm using multiple columns, then this becomes very big in code very quickly. If I have 10 columns and I want to use all 10 of them, then it is much easier to say with dataset plot and then just use the column names if they were variables. So this is the first plot that I make, right? And it's an okay plot, right? I get the idea of what's happening here, right? I can see that the faster a car travels, the further the distance it can drive on a single tank of gas. So that's something that we learned from this. So when we do plots, there are a lot of parameters, and I had, like, during the assignments 4 we already looked at the par, but every plot has more parameters that you can set. But I want to highlight a few key ones, and these are the only ones that if we do the exam, Ugur and Ray. Hello Ugur, welcome to the lecture. So these are the key ones that I want you guys to know. So when we have the exam somewhere in July, you only have to know these ones. You don't have to know other ones, because of course the questions that I'm going to ask you on the exam are only going to be about the stuff that I tell you during the lectures, and I can't assume that you guys are going to read the whole help file of R. But of course there's much more that you can set. So the main ones are PCH, which stands for plotting character. So the default is an open circle. We have LTI, which specifies the line type. The default is a solid line, but you can also use dash lines, dotted lines, dash dot, zigzag, and these kinds of things. LWD is the line width, and this is specified as an integer multiple. So the line width can be 1, it can be 2, it can be 3, it cannot be 1.5. So it has to be a full number, right? An integer number. Col is for the plotting color, and there's many different ways to specify colors. You can use it as a number. So col is 1 is black, col is 2 is red, col is 3 is blue, I think. You can also use the string like we did during the assignment. So you can say color is hot pink or color is orange. You can also use a hexadecimal code, which is very useful when you come from, for example, web design or web programming, where you write FFAA00, right? So then you have FF means full red, AA means like half blue, AA means half green, and then no blue component, right? So you can use that as well. And the colors function gives you a vector of colors by name. So if you just type colors, open close, then it will give you all of the named colors that are in R. Xlab stands for the character string that is going to be used for the X label. Ylab is the character string for the Y label. So it's just the stuff on the X-axis and the Y-axis, so it's the description, right? And again, make sure that when you do an axis, that the axis has the thing that you measured and the unit with which it was measured. There's nothing worse than having a plot where it says speed without anything, right? Is it miles per hour? Is it kilometers per hour? Is it light years per hour, right? You need to have a unit. So these are things that you can give to the plot function, or that you can give to points, or that you can give to lines. But there are also the global parameters, right? So those can be set using the par function. So you can, using the par function, you can set global parameters, and these affect all of the plots that you are going to do from now on until you close the window or until you open up a new window, right? So these parameters can be overwritten. So you have LAS, which we use today, which you can use to change the orientation of the axis label, right? So normally it is written in a standard way, so you have 777, but sometimes it will, you want to have it flipped around, right? So you want to have the it's a 90-degree rotation. BG is the background color of the plot. So we haven't used this yet, but I use it a lot, right? My slides have a black background. So when I make plots like this with a white background, it doesn't really fit my style of presentation, right? So in this case, I would say my background color is transparent, or my background color is a like darker color to have it fit with my style of presentation, right? So the background color BG can be used to set the background color of the plot. MAR is the margin size. So here you specify how much space you want to have on the bottom, on the left side, on the top, and on the right side. So this is different from the axis function, because the axis function is 1 on the bottom, 2 is the y-axis, 3 is the z-axis, and 4 is the top axis. But with the margin size, you go from x, y, top, and then to the right side of the plot. So it follows like a clock, but you start at the bottom. You have the OMA, which is the outer margin size, and this is used when you have multiple plots. So when you have, for example, MF row, if you have, for example, 3 plots next to each other in a window, then you can use the OMA to define how much size there should be between the different plots. Because sometimes like labels start overlapping and you want to give a little bit more OMA, but you don't want to change the margins of the individual plots. MF row and MF col, we already saw them during the assignments. You can just use them to make multi-plots in a single window, right? So it allows you to do 1 plot, 2 plots, 3 plots, 4 plots, and then a 1 column, 2 column, 3 column layout. So if you want to get the current settings, then you can just say par LTI, right? So the current line type or the default line type in my R when I did this is solid. The standard color that it's going to use is black. The PCH, so the magnification of the points, is 1, or the point character is 1. The background is white, and the margins are 5.1, 4.1, 4.1, and 2.1. And we can see that in R. So let me show you guys the R window. So the default margins are 5.1, 4.1, 4.1, 2.1. Right? So bottom, left, top, right. And then we have the MF row. So standard, this is set to 1, 1. Right? So give me 1 row, 1 column, because there's 1 plot in a plot window. Alright, so then different functions to plot. We already saw plot. This makes a scatter plot or other types of plot depending on the class of the object that you're plotting. Because this is the plot is the thing that sets up the window, and after it sets up the window it calls points with the data that you supplied. Lines are so the lines function is there to add lines to a plot, so you give a vector of x values and a corresponding of y values. So lines takes 2 inputs. The first one is the x positions and the second one is the y position of the different lines. And these are points, right? Because a single xy specifies a point on the plot, and then it will draw a line from the first to the second to the third to the fourth. And you can also supply a 2-column matrix. And this function just connects the different dots to each other. Points is just for adding points to a plot. You can use text when you want to add text labels to a plot, and you can use it by specifying x, y coordinates. So you can say, in my plot on 5x and 3y, put this text here. The title is there to add annotations to x, y, the axis label, the title, the subtitle, or the outer margin. So you can override anything. So if you have no x label, you can use title and then specify that you want to use the x label. If you want to plot outside of the plot window, if you want to put text somewhere which is not inside the plot window but outside of the plot window, you have to use mtext. So mtext is margin text, and that allows you to add any arbitrary text anywhere to the inner or the outer margin of the plot. And then you have axis, and axis, we saw the function, right? You can say axis 1, add 1, put something there, give it a string, and that adds just different axis ticks and different axis labels. So that's how you make custom axes for plots. All right, so when we talk about colors, we also have to talk about color ranges. So R has some built-in color ranges, right? Because if we do a heat map, then we can have many different levels in the heat map. So then we want to also have different color ranges. So R defines the following color ranges by default. So you have rainbow, which goes from red all the way to red, with yellow, green, blue, kind of orange, and then it ends up with the red color. So this one wraps around, which is annoying sometimes. For the heat map, it standardly uses the heat.colors. So on the lower end of the spectrum, you have red, which goes all the way to white, like a flame, right? Because if you think of a flame, then the bottom of the flame is like red, and then you have like yellow, and then you have the white part on the top of the flame. We also have terrain.colors, which is more or less when you are plotting terrains. So that's green, and then you end up with like a little bit of yellowish, and then you go to brown, which is more or less mountains, and then you end up with white, which is the snow on top of the mountains. You have topo colors, which is for topographical maps. It's the same as terrain color in a way, but it adds blue colors for sea level, right? So you have like deep ocean, shallow water, green meadows on the bottom of the plane, and then you get like yellow, and then you go to the brownish color again, and then you have like white all the way at the top. Another handy color function is gray, and here you can use it to specify a certain gray tone. So 0 is white, 1 is black, but 0.5 is like 50% gray. 0.2 is 20% gray, right? So it allows you to have different gray colors. Of course, in many cases, for example in here, we want to use transparency, especially when we have things like histograms, because if you want to show the difference between two different distributions, then you have to be able to see both, right? So we can use transparency, then we need to use the RGB function. We need to specify the red component, the green component, the blue component, and the alpha component. So all of these values are between 0 and 1. So 1 red, 0 green, 0 blue is the red color, and then we can specify the alpha. And the lower the alpha, the more transparent a plot is. So with an alpha of 0.8, you can barely see the green behind the red, but with an alpha of 0.4, it starts mixing together, and with an alpha of 0.2, you get a the overlap is even better visible. So use transparency when possible, because it's really useful if you have things which are overlapping each other. So transparency can save you there. And it also allows you to blend things together, which is sometimes really nice. So there's even a lot more colors, because the standard colors in R are a little bit bad in a way, right? If I'm colorblind, then the rainbow colors are horrible, right? Because you have red and green next to each other. And if I'm like blue colorblind, then the CM.colors are even worse, right? Because this just looks like yellow to someone who has this blue orange blindness. So the basic colors in R are pretty bad. But there is this package called R Color Brewer, and it has predefined sets of colors. And these color sets are made to look good in presentations, but they are also made so that people who are colorblind can actually use them and can actually see them. So you can say, I want to have a certain set, and from this set I want to select 2 or 3 colors. So predefined sets of color is the quantitative set of colors, which you see here, which is set 1, 2, and 3, pastel colors, paired colors, right, where you have 2 blue colors, 2 green colors, 2 red colors, which are distinguishable from each other, right? So someone who's colorblind can still see the proper colors. And you have a dark color scheme, and you have the accent color scheme to accentuate stuff. So how do I get these colors? Well, I have to install the package, of course. So install that packages R Color Brewer. But once I have it installed, I can just use library R Color Brewer, and then I say brewer.palette. N stands for how many colors I want, and this is of course based on the palette, right? The set 2 has only 7 or 8 colors, while set 3 has like 11 or 12 colors. Paired also has 12 colors. So N means pick 2, 3, 4, 5 colors from, and then I have to specify from which palette I can choose them. So these are the quantitative color sets. We also have linear color sets, which go from like yellow, orange all the way to red, or which go from orange to red, or which go from blue to green. So these are built-in color schemes which work very well for things like heat maps. And then we have the divergent colors. So the divergent colors are when you have a heat map. For example, if you have a heat map which shows correlation, because these are generally white or very neutral in the middle, right? So if I have a heat map, then you have negative correlations and you have positive correlations, right? So because the correlation can range from -1 to 1, and then you want to use a divergent color scheme so that correlations which are more or less 0 are not showing up in your plot, but the ones which are very strong, so strong correlations, show up as red colors or show up as blue colors. So 3 different color schemes, all of them optimized for people who have who are colorblind. Of course, like there's still some which are bad, like you wouldn't want to use the yellow-green one if you know that the plot is going to be seen by someone who has a red-green colorblind. But they are better colors, and they kind of maximize the intensity and the differences in plots. And a lot of people use them, especially the pastel ones are really nice. Like I love the pastel 1 and the pastel 2. They look really beautiful in plots. Like so if you have like 5 or 6 groups, you just say, well, take the first 5 colors from pastel, and then you have really like nice pastel colors, and you don't have to think about colors yourself. So one of the drawbacks, of course, is that all of these color palettes in Color Brewer only have a limited amount of colors. And often you want to have a very smooth gradient. So that is why they have this color ramp palette function. So you can make a palette, right? So you can say brewer.palette, take 9 colors from blues. So then this would, if I would just plot all these 9 colors next to each other, it would look like this. But I can interpolate or infer the colors in between. So what I'm doing here is, instead of making the plot using the 9 blue colors from my palette, I can say make a color ramp. So, and instead of 9 colors, I want to have 100 colors. So it will infer 91 colors in between the different colors that I have. And this works for any palette. So you can also do this with the pastel colors. So if you have 3 different pastel colors, then you can have it stretch the color range in a linear fashion, which of course is very difficult because colors are not linear. So the color ramp palette is an interesting function because it actually has, so color ramp palette of a palette of colors returns a function which you then have to call with the number of colors that you want, right? So that's why there's 2 of these round brackets, right? So you call the function color ramp palette with a set of colors, and then this returns a function which you can then directly call with the number of colors that you want to expand to. All right, we already talked a little bit about width. So width is a convenient function. It turns columns into variables. And I told you guys this is why the read table and read CSV function have this check name function. Right, so for example, I can write my data ozone to select the ozone column from my data, but I can also say with my data open up, and so you can define a block. So here what I'm doing is I'm saying here within this block I want to have the columns of my data be accessible as if they were variables. So I can just say with my data calculate the mean of the ozone column. Right? Very short, very, very powerful. And we're going to use this a lot during the coming example. All right, so I wanted to show you guys how I build up a plot, but I think that we're going to do a short break first. Yeah, we can do a short break. Yeah, let's do a short break now, and then we can continue after like 8, 9 minutes, 10 minutes. So yeah, you guys get a cup of coffee. I have my orange juice, so perfectly fine. It's really warm at the moment here, so I'm sitting here like sweating, and I closed the window because otherwise you have all of the like, air blowing. But it's really getting hot here. So Yeah, 5-6 minutes. Well, let's do a 10-minute break. So let's be back at around 4 p.m. I forgot what the second break is actually. Um, we did the insects already, and then second break. Well, you guys just have to see it. I forgot which animal I chose this time. I'm in a thunderstorm. Yeah, yeah, I heard. There's also a massive thunderstorm coming our way. But of course, it hits Holland first because it comes from the ocean. So I hope you're not too scared of lightning because, or well, you're generally not scared of lightning. People are generally scared of the thunder. But um, anyway, I will be back in 10 minutes. You guys enjoy the music, and the music this time is called Atmos. I don't know. I don't pick the names of the music. Enjoy the music and whoa, that's really loud in my ears. I hope it's not loud in your ears. No, you can't hear it yet. Let me try that again. All right, let me open up the music. So now you should be able to hear that. And then we go and we do the second break. So I'll be back in 10 minutes. It's soft. Yeah, it's soft for you, not for me. Like I have my volume at like 100, so that was stupid. All right, enjoy the break, and I will be back in 10 minutes. I didn't make it. I didn't make it in time. So the song was too short, or the break was too long. But I'm back. Um, thank you guys for still being here. Let's go back to the lecture. All right. So part number 3. Building up a plot, right? So this is just to have a couple of slides to show you guys how I normally would build up a plot, right? So first things first, I just want to make a basic plot to get an idea of the data, right? So here we plot all of the data from the air quality data set. So one of these built-in data sets in R, right? You load it with data air quality. I think it's built in, so you don't have to load the dataset library, but air quality has 4 or 5 different columns. It has the wind, the ozone, it has the temperature, and I think the month and the day at which the air quality was measured. So the first thing that I want to do is I want to plot all of the points. So I say with air quality, plot wind versus ozone and give it a main, right? Because I want to have ozone and wind in New York, right? That's what I learned from the dataset when I looked at the help file. And then I added some little blue points to highlight one month. So I highlighted the month May, since we're currently in the month May. So with subset air quality, comma, month is 5, right? So the with function is really useful because you can directly throw in the matrix that you want. So I'm just making my subset and I'm just saying points, wind versus ozone, and the color that I want to have them is blue. And this plot, it's okay, but you're not gonna get a Nature publication with this plot. Right, the points are small, the blue color is not visible enough, the axis here is not proper, the ozone is too small, the wind is too small, and this is readable but might be a little bit bigger as well. There's no units in there, so there's still a lot of things wrong with this plot. So let's make it a little bit better. Right, so I'm going to do an empty plot first, because I like making empty plots because then I'm in control. So the first thing that I do is say with air quality, plot the wind versus the ozone, give it this title, and then type is none. Because I don't want to have the black dots plotted to begin with. I want to have an empty plot. And then I'm going to do the same thing again. So I plot a single month, I make them blue, and I do again. So with the subset air quality, the month is 5, plot the wind versus the ozone, make them blue, and then I'm going to plot the other months in the color red. So I'm going to say with subset month not is 5, do these points, so and draw the points, the wind versus the ozone in the red color, and then the plot looks like this. And you can see that this is already better visible, right? You can now start seeing the blue points because the contrast between blue and red is just much better than originally between blue and black. Still, there's a lot of things wrong with the plot, so we're going to add a legend, right? Because we have to explain what the red ones are and what the blue ones are. So I'm going to say add a legend to the top right of the plot. The color here is blue and red, and the legend is May versus the other months. This is wrong. It's May with an I, so sorry for the typo. Still, it's not very visible, right? So I'm going to make the dots more visible. So to each of the 2 point calls that I have, I'm going to say PCH is 19. So here you see all of the default plotting symbols which are available in R. So I'm going to go for 19, which is the circle which is filled. I could have gone with 21, which is also a filled circle, but it has like a little outline around it. But you can use any symbol that you want, because you can also say PCH is Z or I or O, right? Any character works. I could have just used P's and then it would just plot P in the plot. Not just that, you can also use emojis. So you can also say PCH is and then select an emoji, and then everything will be plotted using that emoji, which is a nice feature but not very useful. Well, sometimes it can be really useful. It generally is not. So these are the default plot symbols. You don't have to learn those by heart, of course. I'm not going to ask you what PCH is the triangle, right? That doesn't make sense to me. So of course the plot still looks not good enough, right? It's still very small, the axis, so I'm just going to say magnify everything with 1.5, right? So this is again the same plot, but I'm now first going to set a global parameter to increase the magnification of the text, the legends, and the axis. And I'm just going to first, before I do any of the plots, say par global magnification 1.5. Then the plot looks like this. And now we start seeing that you can definitely see something in the plot, right? Because now we have the wind, we have the ozone, and we have the other months being visible, readable, but still it's not the perfect plot. But at least now for a presentation, this is something that you could show without being ashamed of yourself. So one of the things that we might want to do is we might want to highlight a single point by adding an arrow, right? And how do we add an arrow? Well, we can use the arrows function. So the arrows function takes 4 parameters. It is the x at which the arrow should start. Then we have the y at which the arrow should start. So here this point is 3.4, 140. And then the next one, so the point that we want to point to, so the top of the arrow here is 3.4, 165. And people always ask me, how do you find these positions? And you just have to kind of look at the plot and just try some values. There is no way to have a custom arrow pointing to a plot that will always look good. So you have to find the coordinates. In this case, I'm going to make the arrow orange, and I'm going to make it fat so that it fits kind of the style of the whole plot, which is like really fat points in the plot, right? So line width is 3, and then I can point at a single point here if I would think that that might be interesting. So besides that, in a lot of plots, you also want to add the best fitting line, right? So you want to add a red line for the red dots, and you want to add a blue line for the blue dots. So you want to fit this line, best fitting line. And a line is defined as the y position of the line is the intercept of the line plus a beta, so a directional coefficient, times x. And for this, we need to use the model. So we need to create a linear model. And how do we do this? Well, we can do this using the width function very easily, right? So I can say width, and I subset my air quality to be the 5th month. So I'm going to say May, right? So take all of the May points, and then I'm going to do a linear model where I say that the ozone concentration is dependent on the wind, right? Because that's the plot that I make here. I say that ozone is my response variable and wind is my predictor variable. And then I can take from this model, and this is a little bit of a trick, right? From the model I can take my A parameter, so the intercept, and that is stored in the model because model is this complex object which also has its custom plot and print functions. But I can say from the model, from the first element of the list that the model consists of, take the first element, right? So that's why you have double square brackets 1, select from model, treat it as a list, select the first element, and then select the first parameter. And this is always the intercept of the model. The second intercept of the beta of the model can be found also in the first element of this list, and then it's the second part. So A is the model, so the intercept is this from the model, and B, the directional coefficient, is specified in this part of the model. And I want to make my line, I want to make it blue, line width of 3, line type is 3 because I want to have it dashed, and then it will add this blue line to the plot. And for the other months, it's the exact same thing, so I'm just going to say width, the subset of air quality, where the month is not the month May, make a linear model of ozone versus wind, and then I can take the model parameters and I can just use those directly using the upline function to draw a single straight line into the plot which adheres to these line parameters. Right, so it's very easy to add the best fit line, and what we can see that in the month May, the relationship between ozone and wind seems to be less strong than on the other months, right? Because the directional coefficient for the month May is lower than in the other months, because this line just goes down much quicker than this one. So this one has a stronger directional coefficient, so to speak. Good. So are we done? No, of course not. We still need to make sure that the x's are okay, right? These numbers need to be flipped because we want to have them in kind of a readable direction. We still need to add units to the different axes. The arrow that we use still needs to be mentioned in the legend. We need to mention the two lines that we added into the legend. The legend text is a little bit big in this case. We might want to reduce the magnification of it, and we might want to look at the margins as well, because of course we have a big white margin on this side which we're not really using, which could be made smaller. Also the margin here might be like a little bit too big, and so there's still a lot of little tinkering that we can do. And that's the thing with R. Making a plot is easy. Making a beautiful plot takes time, and a lot of time sometimes. Good. So I also wanted to show you guys how you can do multi-base plots, right? Just to show you how powerful this width function is. So first I'm going to set some parameters. So I'm going to say I want to have mf row. So I want to have multiple plots. I want to have one row, 3 column. I'm going to change my margins a little bit so that it fits a little bit better. And I'm going to also kind of fiddle around a little bit with my outer margins. But that's not the interesting part. The interesting part from this slide, and what you should remember, is that we told about this block, right? That you can do width, and then you can have a block in the second part of the width function. So I'm just going to say with air quality, plot the wind versus the ozone, plot the solar radiation versus the ozone, plot the temperature versus the ozone. And every time that I write wind, I save myself typing air quality dollar. When I type ozone, I don't have to type air quality dollar. If I would take the same code and not use the width function, I would have typed the word or the word air quality 6 times instead of just once. And that is the power. And I have this curly bracket open, curly bracket close. So here I'm starting the block, and here I'm ending the block. And within this block, every time that I mention wind as a variable, it realizes, oh, I have to go to the dataset air quality and then take the column wind. So a very, very powerful function. And here you also see me using mtext to put some text on top of everything, right? So you have the different mains, so the different texts for the different plots, and then you have one description on top saying ozone and weather in New York City, which is relatively small here, but trust me, it does say ozone. And so you can use the m text to put stuff in the outer margins of the plot. That's why the OMA here has a 2 on the top, because it needs some space in the outer margin so that I can put my kind of global header that for all the 3 different plots in the outer margin. Good. So one of the other types of plots which people love and are very easily to understand is the pie chart. So pie charts in R are done with the pie function. So the pie function takes the slices, which is the size of the individual measurements, right? So here we have measured 5 countries: the US, the UK, Australia, Germany, and France. The US got 10 points, the UK got 2 points, Australia got 4, Germany got 16, and France got 8. So these are the slices. So it will automatically scale those to be 100%, right? Because these numbers don't add up to 100. That doesn't matter. R will make sure that they add up to 100. However, we might want to make the labels in such a way that we show not the number, but that we show the percentage. So you can do that by saying, well, take the slices that I have, divide them by the sum of the slices, and then multiply by 100. Right? So that's also how R calculates how big each of these slices of the pie should be. So it's just calculating, or just doing each slice divided by the sum, which is just the standard way to calculate percentages. Then I'm going to add the percentages to the labels, and then I'm going to add a percent symbol afterwards, so just that it looks a little bit better. And then I just call the pie chart function, giving it the slices, giving it the labels, and I say here that the colors should be the rainbow colors. And how many rainbow colors do I need? Well, I need, in this case, 5, and 5 is of course the length of the labels. And then I give it a main saying pie chart of countries. right? So this is how you build up pie charts. In this case, if I would normally show it on my plot, pie charts I generally make with a transparent background, and then I just use my pen to make the background for the individual legends and titles. I make them white in the background. You can see that in, I think, the fishy data lecture. But this is how you can make very easily pie charts in R. One of the things that you use a lot as well in biology is dendrograms. So I had to show the relationship between different objects. So here we use the car data set again. And here what I'm going to do is first I'm going to do a hierarchical clustering. So from the empty cars data set, I'm going to calculate the distance matrix. So it's just calculate for each car how different it is to all of the other cars in the data set. And then I'm going to use hierarchical clustering to cluster my data, and then I get a hierarchical cluster object which I call HC. And then there's a plot.hclust. So when I call plot, it calls a custom plot function to make a dendrogram, which looks like this when you just do the standard hclust clustering. Of course, you can, in the distance function, you can specify which measurement you want to use. Do you want to use Euclidean distance? Do you want to use Manhattan distance? And in the hclust function, you can also set what kind of clustering you want to do. If you want to do single clustering or complete clustering or up GMA clustering. So these are all parameters. But just for the example, I just use all of the default parameters. And then it looks like this, which is quite okay. But generally you don't, if we're thinking of biology, right? Then generally you don't want something to stop halfway. Because in biology that means that the Maserati Bora died out like 175 years ago. And that because in biology, if something is still alive, then the line should go all the way to zero. Because I measured an animal today and it's still there, so it didn't die out. So if you want to do that and you want to pull down all of the labels, you can say hang is -1. And when you say hang is -1, all of the labels are more or less put on the same level. So you get a standard, more or less, looking dendrogram. So hang allows you to kind of make it so that all of the labels are on the same row. Of course, we can also make a dendrogram object. So there's a difference in R between a hierarchical clustering object and a dendrogram. But we can take a hierarchical clustering and transform it into a dendrogram by using the asDendrogram function. So here I'm going to say a hierarchical cluster dendrogram object. Dendrogram has its own plot function. So there's a plot.dendrogram. So I can say plot HCD. It will see that the class of the object is dendrogram because we just changed the class. And now I can specify what kind of a type I want to have. On which differences is this diagram based? For the cars, let me see. MT cars 1 to 10. So empty cars has miles per gallon, the number of cylinders, the disp, don't know what that is for a car, horsepower, the D-rad, the WT, the Q-sex, the VS, the AM, the gears, the carb. It just has all kinds of measurements on cars. I would not know anything about car. I haven't owned a car in my life, so but hey, it's just measurements on cars. It works the same for example, the ozone and the for the other data set. It's just that there are much more cars, right? You could do a clustering with the versicolor and the different irises as well, but then you would only have 3 things, and I just took the car data set because it has a lot more cars in there than 3 irises or 6 measurements on air quality. But yeah, so there. But if you're interested in it, you can just do question mark empty cars, right? And then you get the help file. Let me show that in the window that you guys can see. So here is the data set description. right? So we see that it is Motor Trend Car Road Test. The data was extracted from the 1974 Motor Trend US magazine and comprises fuel consumption and 10 aspects of automobile design and performance for 32 automobiles, which are the 1973-1974 models. So it describes everything, so miles per gallon, number of cylinders, displacement, gross horsepower, rear axle ratio, the weight, the quarter mile time, so probably how fast it is, the engine type, the transmission type, the number of forward gears, and the number of carburetors. And then if you want to cite this data set, they provide the source as well. So this is the citation for the data set in case you figure out something and you want to publish about it. So R is really good in documentation, right? So anything that you want to know about any of these data sets, also the air quality data set has all of this information inside. So that's really, really useful. All right. Good. So triangle plot, right? Looks a little bit different. Same clustering, same distances. Nothing has changed in the plot. Right here we see that this cluster here is at like 125 and it should be here at 125 as well. It's just a slightly different visualization. So here we use the triangle visualization of the dendrogram. And this, of course, in biology, you generally tend to use triangle visualizations. I don't know exactly why. It's just in phylogeny and phylogenetic analysis, people tend to prefer triangle dendrograms compared to the standard like square dendrograms. I don't know why, but that's just every field has its own way of visualizing things. So this is one of the hardest parts because you can also color dendrograms and that makes them really cool. But coloring dendrograms is really hard in a way. So I'm going to try to explain how you can color your dendrogram, but it's a lot of trial and error. And this is because you have to write a function, right? So to add a color, we need to write a function, and this function is going to be applied to every node and every edge in the dendrogram. So it will look at this node and edge, see if it applies, and then change the attributes of this node. It will look at this edge, and then we can change the attributes of this edge if it matches. And we can do that for all of them. So we can just walk ahead what we write the function, and then we use an apply function to apply our function to every node and every edge in this dendrogram. So, and we can use the attribute function to set node attributes. And definitely look at the dendr apply function because there are some very good examples in there. But I'm going to kind of show you how normally you would do this. So the first thing that I want to do is I want to only color the lower part, right? So I want to color the names of the cars depending on in which cluster they belong. So of course I need to find a way to define a cluster. So I'm going to be really lazy and I'm just going to say cut tree. So the hierarchical clustering, cut it in 4 different parts. So find a cutoff where when I use this cutoff, it will make 4 different groups. And then for each of these groups, I'm going to assign a color. So here I use the hexadecimal way of defining a color because this is how many people think about colors, just so that we don't have to type in gray and hot pink and orange and red again. And then I can have this function to color the leaves of the dendrogram because these things here are called leaves. These are nodes, these are edges, these are also nodes, but they are leaf nodes because they are at the end of the dendrogram, right? If you would take this plot, turn it upside down, then the tree would start here with the root and then it would grow up into a tree. So these things on the bottom are the leaves. So I'm going to write a function which is called collab, so color the labels. It is a function which takes as an input n, and n here stands for node, which is poorly chosen because it is nodes and edges. So the first thing that I have to ask, am I in a leaf? So is the current thing that I'm looking at, is it a leaf? Is it all the way in the bottom of the tree or all the way on the top of the tree, right? If this is the case, I want to get the attributes of this node because I need to know the label. right? Because I need to know which car I'm currently looking at, right? So I'm going to say get me or give me the attributes of the node, and I'm going to store this in a variable called a. So then I'm going to say the names of the cluster members, right? Because it cut the tree in 4 different groups. So this is a cluster members is a 4 is a list with 4 vectors in there. The first vector contains the names of the individuals or the cars which belong to the first cluster. The second one, the names of the cars belonging to the second cluster. So I'm going to say which names of cluster members is equal to the label that I'm currently looking at, which one is it, and then take this one from cluster members. And this is then the cluster that we're currently in. Right, so this will be either cluster 1, cluster 2, cluster 3, or cluster 4. And then I'm going to say, update the attribute of the current node that I'm looking at using the node par, because those are the node parameters. What do I want to do? Well, I want to use the current node parameters of this node, right? Because I don't want to change the font size. I don't want to do other things with it. I just want to add something. What do I want to add? I want to add a label color. And which label color should this car have? Well, it should have the label color corresponding to the cluster that it is in. And then I close it. So I'm only updating leaves here. I'm not updating nodes, I'm not updating edges, but you can. You can have if it is a node, if it is a leaf, if it is an edge, you can update it. And in this case, we just want to return n after we're done. Because if we would not return n, then it would eat up the whole dendrogram, because then nothing would be returned. Good, so now what I need to do is I'm just going to use the Dendr_apply function, which will apply to our dendrogram our function that we just created, color the labels, and I'm going to give it the HCD, so the hierarchical clustered dendrogram. And now I have a new object which is called class dendro, which is updated, so now you can see the different colors, and I don't, in the plot I don't specify the colors because the colors themselves are in the class dendro, the colored dendrogram. So I'm just going to plot it and give it a main, and again I'm going to use triangle. And here we can see that indeed it uses 4 different colors for the 4 different groups. And this is really, really hard, because if you want to make a really, really cool looking dendrogram saying that, oh, I want to actually have these be dotted lines, and then I want these to be like solid color lines with different color, then you have to do a lot of programming, and every time you have to figure out where am I in the tree, am I above or below a certain threshold, am I a leaf or am I a node or am I an edge, and then you have to update the parameters accordingly. But just to give you an example that how you do it, so you have to write a function and then you apply this function to every element in the dendrogram using Dendr_apply. So this is like the standard apply function, but now for dendrograms. Good. If you want to have even more fancy phylogenetic tree, you can use the APE package. So the APE package is a package which is specifically designed for phylogenetic trees and other types of plot. So it provides 4 different plots. It's just a basic tree plot. It has the cladogram, the unrooted plot, and the fan. And we take our hierarchical clustered object, so the thing that comes out of the hierarchical clustering, and then just say as philo instead of as dendrogram, because APE defines its own type, its own S3 type called philo, and all of the plot functions work on a philo object. Fortunately, they provide an as philo, so you can convert a clustered object into a phylogenetic tree. So we can say plot as philo HC, so the clustering, and then we can plot it as a basic tree, we can plot it as a cladogram, as an unrooted tree, or as a fan, and this is how it looks. So a basic tree looks like this, because in phylogeny we always plot from left to right, right? Because this is the earliest time point and this is the newest time point. This is a cladogram. So a cladogram is a basic tree, but now using a triangle layout, and this is what you generally see in papers where people compare viruses or compare sequences, right? So then you make a cladogram. This is the unrooted tree. So the root is, there is no real root. Like this is the root here, or not really, because it doesn't really have a root, but it shows you the four main kind of clusters in your data. And you can also use the fan representation. So the fan representation is again like the cladogram in the basic tree. It is a rooted representation, so it has a single point of origin, and then it just spreads it out in a fan. And these are really nice when you have a lot of objects. And these look really cool when you start coloring them. Again, the phylogenetic tree can be colored as well. So you can spend some time writing a function which you can then apply to the phylogenetic tree to update the leaves and give the leaves colors based on, for example, their the cluster that they belong to. Good. All right, so for 30, I still wanted to show you guys a real life example of something that I did, well, not recently, but some time ago. And this is plotting data on chromosomes, or on a kind of chromosomal representation. So we are going to plot chromosome data, and then we're going to add information to the individual chromosomes, because we're from biology. And of course, like, if you're not from biology, it's not as useful, but the way to do this for your own data is probably very similar, right? You might not have chromosomes, you might have companies, or you might have political parties, or you might have biblical figures if you're from theology. In the end, it doesn't matter. You want to visualize this, right? And chromosomes are the thing that I normally visualize, so that's why the example is about chromosomes. So we want to plot chromosome data, and then we want to add some information to the chromosomes. So we have three different types of data. So we have our markers, right? So we have positions on the chromosomes that we have measured. So we have the location. So this marker is on chromosome 1 at a certain position. And we have some sort of statistics. For example, this marker is up, or this marker is down. We have, for example, genotypes at these markers, and we might have things like chromosome length, right? So we might have much more data than just the markers. So in this case, we're going to ignore the genotypes because we are not dealing with multiple individuals. We have a statistic, we have a location of this statistic, and we have a length of the chromosomes that we want to draw. So the first step is to define our chromosomes. If you're a mouse geneticist like me, or working on mice mostly, then you would know that a mouse has 19 autosomes, so 19 autosomal chromosomes, and we have the X chromosome, the Y chromosome, and the mitochondrial chromosome as well, right? So the one that you get from your mother, the one that you get from your father, and then the one that you get from your mother again, but now not in the nucleus, but in the mitochondria, you know, the powerhouse of the cell. So first we read in some of the data. So I made here a chrinfo.txt, which I just went to Ensemble, and I looked up for mouse how long is each chromosome, right? So I made a little table which I load in using read table. I could have just hard coded it as well, but this way the code is more generic, right? I can use it now for any chromosome because I'm not going to assume that I have like 22 chromosomes. I'm just going to assume that I have n chromosomes. So to show you a little bit of how this looks, well, this is just a table which has two columns. The first is the chromosome, and the second column specifies the length of the chromosome in base pairs in this case. And then we have our statistics data, right? So we have our ratios, for example. So in this case, we're looking at different genes which are located on different positions in the genome, and then it has a ratio, meaning that it is up or that it is down. So a positive ratio means that it's upregulated compared to standard, and a ratio is 0.7. That means that it's downregulation compared to standard. Right, so in this case we have the first three genes listed. So this gene is located on chromosome 1 and it's at this position, and this is the ratio that it has, 0.78. So this is the data that we want to visualize on top of the chromosome. So the first things that I do is first I create an empty plot. right? Because I did my drawing and I drew how I wanted to have it, and I figured out, well, if I want to do a drawing, I first need an empty piece of paper. Not just entirely empty, because when I took my piece of paper, I actually had like this paper with lines on there. So just to do that as well, what I did is I made some lines. So I'm first trying to figure out what is the scale of my x-axis, right? So the x-axis runs from 0 base pair all the way to the maximum length, which I just get by asking the max of the chromosome info from the length column. And this is the length of the maximum chromosome. And of course, here I have on the x-axis, I'm going to plot the chromosomes one by one. So I have here n chromosome info. So the number of rows of the chromosome info file gives me how many chromosomes there are. And then I'm just going to set up an empty plot saying plot x is 1 to the number of rows of chromosome info. The y length is from 0 to my length. Do not plot these 2 points that I specified. Just give me an empty plot, so t is none. Don't give me a y-axis. Don't give me an x-axis, x label. Don't give me a y label, and don't give me an x-axis. So just disable plotting of all of the axes. And then the first thing that I wanted to do was have some lines. So I just made like little dotted lines in the background to kind of have an idea how far we are inside of a chromosome. And I do that every 10 million base pairs. Because if you look at the data here, then like the first gene is at 7 million base pairs. No? 72 million base pairs. Then the next one is at 132 million base pairs. Right? So the scale is very big. Right? It's in millions. So I'm just going to say make a sequence. So I want to have horizontal line going from 0 to the maximum length of the chromosome, and I want to step by 1 times 10 to the 7th, which is by 10 million. And make them light gray and make them dotted. They look a little bit bluish here, but they are light gray, so that's okay. So the next thing is to add the chromosomes, and to add the chromosomes I'm going to use the lines function. So the lines function draws a single line, and it needs an x vector with 2 elements, the x start and the x end. So this is easy, right? If we're on chromosome 1, we want to put it on 1. If we're on chromosome 1, then the x in both cases for the beginning and for the end position will be of course 1. On chromosome 2, the beginning and the end will be at x equals 2. And y is the vector with 2 elements, the start position of y and the end position of y. So I'm just going to say for n in 1 to the number of chromosomes, or to the number of rows of the chromosome info, and I'm going to open up my block, I'm going to close my block, and I'm going to say make a line starting at n, n, right? Because the start x and the end x is going to be 1 or 2 or 3 or 4. And then the y position is going to go from 0 to the length specified in this table. I want to make a line, I want to make it black, I want to have the line type being 1 and the line width being 2, and then it plots the chromosome one by one on the plot. And then I want to add the ratio data, right? So what am I going to do? I'm going to just apply to all of the data that I had. So that's the data file where I have chromosome, where I have gene, chromosome, position, and then the ratio. So the first thing that I have to do is say apply to all data to the rows a function of x, and x here is the current row that I'm looking at. So I'm going to match the chromosome name of the current row to the chromosomes variable that I defined, right? Because they are not all numeric. You also have chromosome X and you have chromosome Y and chromosome MT. So, and then I'm going to take the Y log, which is the start position, right? Which is the start position or position in this case of the gene. So it's a little bit messy because this would just be X pos. Because the code comes from where I had start and end positions. I'm going to make a color, right? Because I want to have stuff which is upregulated in one color, so a ratio which is higher than 1, and stuff which has a ratio lower than 1, I want to color them differently, right? So I'm just going to say, well, when the ratio is equal to or larger than 1, this is true or false for every element in my matrix, for x, right? It can be that the ratio is above or below 1. So if it's higher than 1, then I'm going to convert this as a numeric. So this will give me a value of 0 and 1. And I'm going to add 1. And this is because the color starts at 1. There is no color 0. Color 0 does not exist in R. So you have to have always 1. So if this would be false, right, then as numeric, false would be 0. 0 is not a color, so I'm going to add 1. And if this is true, then as numeric true is 1, plus 1 is 2. And then I'm just going to draw the current point. So I'm going to say draw a point at the X location that I just figured out, right, by matching the chromosome name to the chromosome. Add a Y location, right, so where do I want to add it? I'm going to use the minus symbol as my plotting symbol. I'm going to give it a color, and I'm going to magnify it a little bit to make it a little bit more clear. And then I already start seeing some information on my chromosomes, right? So I can see that something is down here, something is up here, here something is down regulated, here something is up regulated. Of course, I still need to do a lot to make the plot more beautiful, right? I need to add the axis. So I'm going to say axis on the x-axis, use the chromosome info 1, which is the names of the chromosome, plot these at 1 to the number of chromosomes. LAS is 1, so plot them normal, like normal people read them, and then magnify the axis by 1.5. I'm going to add a second axis. In this case, I'm going to write stuff as millions, so I'm going to take the length and divide it by 1 times 10 to the 6th, and then I'm going to plot that at the same position, and because in my plot I want to say 10, 20, 30, 40. I don't want to say 10 million, 20 million, 30 million, right? Because I'm just going to do it in million base pair. So I'm just going to divide the current length or the length of the chromosome. So I'm going to make a sequence from 0 to the maximum length of the chromosome, stepping by million divided by a million. And then these are going to be plotted at these positions, which is the same thing. And then I'm going to, except not divided, of course. And then I'm going to do the magnification, and I'm going to do the loss. And I actually want to add a legend to the plot, saying on the top right corner, say up, say down, fill it by 1 and 2, and then magnify it by 1.2, and then it looks like this. Right, so now I've kind of finished my plot, so now know what the different colors mean. I know the chromosomes, and you can start seeing that the different names of the chromosomes are there, and now here we have the positions in tens of the 0 megabases, 10 megabases, right? So here we see a gene located at like 71 megabases, something like that, which is upregulated. And here we see something which is downregulated. Are we really finished? No. There are still a lot of things which are not correct, right? So one of the things that we can, the things are a little bit, we don't, this one needs to be here, right? So we don't have a title. You can see that there's the bar here at the bottom, the background of the legend is transparent, which I should put to white to make sure that there's no line in the back. There is no X label, right? The X-axis has no label, the Y-axis has no label, so there's still a lot of little things that I need to solve to make this a good looking plot, right? But hey, you can start seeing how I build a plot. So first draw the lines, then draw the chromosomes, and then on the chromosomes draw the data that I have. And that is the same for any type of plot that you do. And of course you do want to have code which is generic, right? So if you write the code once, you don't want to hard code how many chromosomes there are. You don't want to hard code how long each of the chromosomes is. All of this data should come from individual data files, and you should always, when you write code, instead of saying for x in 1 to 5, what you want to say is for x in 1 to the number of rows or the number of columns of a certain object. Right, so there's still a lot of things that need to be done with the plot, but at least we have visualized our data, and this is a completely new visualization which is not available in R. Good. So my procedure to plotting, I hope it's clear now. It's a multi-step procedure. I first draw them by hand, and then I start thinking how to make them from the data. So I'm drawing a square here. How does this square relate to my data? And first I do the layout of more or less static things like chromosomes or grid lines or stuff which is in the background. And only after I am more or less happy with this basic plot, I start drawing in the data. What exactly does hard coding mean? Oh, hard coding means that you put in the number. So instead of writing the number of rows of the matrix, you write 15, right? Because you're saying this is my data set, right? So hard coding would mean that in your script you have the length of a certain chromosome being just a number in there. You always want to avoid that. Data should come from data files. So you should load in how many chromosomes there are, what their lengths are, instead of more or less hard coding saying that the number of chromosomes is 5. And I'm going to write a for loop saying 4x in 1 2 5. No, what you should say is 4x in 1 2 the number of chromosomes. Right? Because when you load in a new data set, which is not on mice but on humans, then all of a sudden you have a different number of chromosomes. If you load in the data set on Arabidopsis, an Arabidopsis plant only has 5 chromosomes. Right? So when you write plotting code, you want plotting code to be based on the data that you have. And so it should not say there are 5 chromosomes or there are 6 other things, right? And that's what I mean by hard coding. On which differences is this diagram based? So this diagram is based on some data that we did using microarrays. So they're differentially expressed genes between the Berlin fat mouse and the B6N mouse. But it's the plotting code that I made in the end is generic. So I made these plots for differential expression of genes, but you could also look at, for example, the CG content at certain positions, see if it's significantly lower or higher than the number of C's and G's in the average genome. But then by making plots in a way which is generic, you will save yourself a lot of time in the end. It's slightly harder, right? Because saying for x in 1 to 12, take the first column, take the second column, take the third column, take the fourth column. But then you put yourself into a corner, right? Because now once your data set gets updated and you all of a sudden, instead of 12 columns, you have 15 columns, then it will only do it for the first 12 because you hard coded the number 12 as being the end of the range. And you should never hard code numbers on it, like scripts should not have numbers in there, as few numbers as possible. Numbers should come from data files. So that's the hard coding problem. It's not that it's hard to code, but it's fixed in the script as a single number, and you should try to avoid that. All right, we already had this slide, so make plots in first draw them, think of how you make them from the data, look at what the things are that are not that you can get from data files, and then do the layout of the static things in the background first, and then go to the data which you then put on top. Is that actually, like, do you understand what hard coding is now? Just gonna wait to see if I get a yes or a no. Because like in the end, I can show you a couple of examples of where you hard code stuff which you should actually not do. It's the same as saying my matrix, comma 6, right? This is worse than saying my matrix, comma speed, right? Because The second piece of code will always take the speed column, while this one might take the speed column if the speed column is the sixth one. But if you resave your file in Excel and you just added a column additional, or you removed a column, then now all of a sudden the stuff that you're plotting is not the stuff that you're plotting, right? So here you're hard coding 6, saying that speed should always be in the sixth column. But only you know that. And you can't tell other people that, no, your sixth column should have been the speed column. No, but it's better to just write my matrix comma speed, right? Because then you're always selecting the right thing, the thing that you want. All right, so all in all, some advice in the end: it takes time to make things beautiful. Make sure that you have a flexible plotting code, right? So that you take columns by their names, that you iterate by number of rows or number of columns of a data object instead of saying 1 to 5. Make sure the figure is reproducible. That's the main thing in science, right? If you copy paste in the code after deleting a column from the data set, it should still generate the exact same figure, unless of course this column is absolutely necessary, right? In the code that I wrote here, deleting the first column with the name of the gene will not affect the plot, because it's not used in the plot, right? So in theory, you should write code in such a way that you can delete columns from your data set, and still the same figure should come out. And that is kind of how you can kind of figure out if you've hard coded. And one of the things that I want like to stress is that I always make 2 versions of every plot that I make. I make one for PowerPoint, for presentations, and I make one for PDF, which is a lot of extra work, but it is necessary, because the requirements for a plot that is being printed in a journal on a piece of paper is different from a plot that you show in a PowerPoint presentation. There are different requirements. Like on a PowerPoint, everything needs to be much bigger, because people in the back of the room also need to be able to read it. In a paper, it needs to be readable, but you can go much smaller, right? You shouldn't go too small so that someone needs to have like a lupa to read the thing, but as long as it's readable, it's good. But on a PowerPoint, people in the back of the room still need to read it. Not just that, if you have PowerPoints which you present on YouTube, there are some additional requirements that you want as well, because YouTube is different because people are either watching on their phone or on their tablet, so you don't have to exaggerate things as much as if you would present in front of a crowd of people, where some people might be like 20 meters away from you. A good plot has clear axes, clear labels. It has a good representation of quantities. You always have to add the units to the plot: speed, kilometers per hour, miles per hour, light years per hour, or, well, not light years per hour, but light years, right? That's a speed unit in itself. So always add the units. Is it grams? Is it kilograms? Always add a legend, and the legend should contain everything that is in the plot. If there's an arrow in the plot, the arrow should be in the legend. If there's a line in the plot, the line should be in the legend. And if it is available, if you can calculate it, add error bars. Mostly you have errors, and you have errors in your measurements, because even measuring your own hand will have an error, right? If I measure it now and I measure it another time, then every time it will be slightly different. So if you can, add error bars and standard deviations to your plot, because a bar plot without any error bars does not show you what you want to show, right? You want to represent your data, and if there is any uncertainty, show the uncertainty in the figure that you are making. Good. So that's it for me for today. I hope you guys learned something about plotting in R. I wonder where the violin plot went. We didn't see a violin plot. I made a whole slide for a violin plot and then... What? What happened? What happened? I'm so confused. Holy moly, where did, like... I'm showing you guys an old version, I think. That is so horrible. I'm going to show you guys a violin plot because I made one and I did my best. I actually selected the colors. What? That is so horrible. Because I wanted to talk about the violin plot because it's such a nice plot. Let me actually look that up. Where the hell did my violin plot go? Na, 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 na. Yeah. It ate my slide about violin plots. What the hell happened here? Or did I did it do it in lecture 4 or something? No, I didn't show the violin plot in lecture 4, right? I'm so confused. I did. Or I added it to the wrong lecture. I'm confused. Did I guys show you this one? I'm really confused now. Alright, so this is a violin plot, right? It's much better than a bar plot or a box plot to show you the distribution of your data. And I don't know. Did I put it in the plots lecture? Last week. Okay, good. So I did show you guys the violin plot. Alright, but don't use box plots, use violin plots. They're much better. So, as a tip. I, I really thought that I added it to this one. Alright, doesn't matter. Doesn't matter. It's late, it's warm, like I'm sweating like mad, and I'm not thinking very straight anymore. But yes, you did. Okay, very good, very good. All right, then I would like to thank you guys so much for staying until the end, and I hope you guys are sitting outside with the laptop, and that you guys are at least enjoying the sun. Well, not you, Misha, because you told me you had a thunderstorm, but I hope that at least the students were smart enough to follow the lecture from the nice side of a pool or underneath a tree in the park, and did not have to spend it inside. Yeah. Even though you're a nerd, you don't have to look like a cave dweller that lives in his mom's basement, right? That that's not necessary. Nope, inside with a ventilator. Well, that's also a good thing, right? I actually was hoping that I could keep the window open and not like melt, but good. So with that brain fart, and if there's any questions, then feel free to ask. I already uploaded the assignments to Moodle. I also uploaded the additional assignments to Moodle, and I would. I'm gonna wish you guys a lot of luck doing the plotting assignments. They're not that hard. Some of them have a little tricksy thing, like a little trick. But if you can't figure out the trick and you're spending too much time, um, drop me an email and I'm more than willing to help you guys. So for everyone who stayed until the end, thank you, thank you, thank you. And I will see you again, not next week, because next week is a holiday, but I will see you the week after. So lecture number 6 will be on the 2nd of June, if I still have my YouTube channel. Because I submitted some people actually, someone stole my video and uploaded it on its own channel. I submitted a copyright takedown request, and then Google said, or YouTube said, like, you are submitting a fraudulent request. So I hope that everything goes okay and that they realize that I am actually the creator of the video and not the other guy that just stole it and uploaded it like 6 months after I uploaded it. But everything should be fine. So I'm hoping that I will see you guys in 2 weeks. So we will see each other again on the 2nd of June. with lecture number 6. Lecture number 6 for good measurement will be about statistical testing. So we are finally hitting the statistics part. So lecture number 6 will be statistical testing. Then we will have regression, probably regression models, so complex regression models with repeated measurements. And then we will do some algorithms and functions, R packages, and these kinds of things. But I'm hoping to see you all then on the 2nd of June with lecture number 6. For now, enjoy the rest of the afternoon, and thank you guys for being here, for liking the video, and for being active in chat and just asking questions. Really appreciate it, and enjoy the rest of your day, and enjoy the rest of the beautiful weather for this week. And see you next time.